and it is a pleasure to welcome one of my colleagues, Dr. Amit Shukla, for the first talk. Dr. Shukla did his PhD in astrophysics from IIA Bangalore in 2013, and his main research interests are active galactic nuclei, blazars, radio galaxies, multi-wavelength and multi-messenger astrophysics, in general, high-energy astrophysics. So without further ado, I would like to request Dr. Shukla to start his talk on gamma ray astronomy. Dr. Shukla.
Thank you, Siddharth, for kind introduction. I'll just share my slides and then start the lecture. Is my screen visible to everyone? Yeah.
Yes, Amit, now it is visible.
Okay. Thank you very much, Siddharth. So, hello everyone. As Siddharth said, my name is Amit Shukla. I am a assistant professor at IIT Indore, and I'm a high energy astrophysicist. Mostly work with blazars and active galactic nuclei and some of the high energy photons. So I know that you people have gone through with a lot of different topics from radio astronomy to optical astronomy, cosmology, etc. And for all these astronomies, I would just like to say that you have a very good number of photons coming from the celestial sources, either a star or from a galaxy. However, in the case of gamma ray astronomy, we are sort of deprived in terms of photons. We only get a few photons, or I would say handful of photons. Even you sometimes you count those photons on your fingertips. Let's say we can say if I observe a source in a night with my telescope in gamma ray energies, I may end up only say 5 to 6 photons. And using those photons, we are actually trying to understand the nature of the source which is emitting those photons, and further making advancement in the field. So today I will be discussing mostly about gamma ray astronomy. I would like to discuss mainly two kind of telescopes, and I will also try to explain how these telescopes are making advancements in the field of gamma ray astronomy, in the field of pulsars, in the field of AGN physics. And these two telescopes are mostly, one is the space-based telescope, which we call it Fermi-LAT, which already I have shown in the right corner of my first slide, or the slide which has my name and the title of the talk. And there is another kind of telescope I have showed in the left, which is a FACT telescope, which is a very specific kind of a telescope. It's called atmospheric Cherenkov telescope, and we have very handful of these kind of telescope. If I talk globally, we have 4 telescopes of this kind globally, and right now in India we have in the phase where we are actually commissioning one of the similar kind of telescope. So including that telescope, we only do have 5 or 6 telescope of this kind, which we call it atmospheric Cherenkov telescopes. These technologies are quite different from the optical astronomy techniques. So I will try to discuss some of these interesting aspects of high energy astrophysics. And in the middle, I have shown another image of one of the active galactic nuclei, which we call it Centaurus A. Generally, the gamma ray emission from active galactic nuclei is considered to be emitted through their jets and somewhere very close to their central engine, which we believe it could be a supermassive black hole. However, very recent results from Hess collaboration has also showed us that the emission of very high energy gamma ray be can happen or can originate much far away from the event central engine. So I will try to cover some of these interesting aspects in today's talk. So let's start our journey. Okay, so as I said, that till now you have already learned about several different type of astronomies, including optical, radio astronomy, X-ray astronomy, and a different kind of sources such as active galactic nuclei, pulsar, different kind of stars. And you can observe these particular astronomical sources with different wavelengths. So let's start with some of the telescopes. So in the first slide, I have shown you the electromagnetic spectrum, where the x-axis is basically the wavelength, or you can say wavelength or the energy. So at the very left, we have a gamma rays with the very short wavelength, and then the wavelength increases and energy decreases up to radio wavelengths. So we do have several telescopes at radio wavelengths such as VLA, GMRT, and then to observe infrared wavelengths. We also NASA has a very interesting telescope which they actually fly on one of the aeroplane. And then we have several optical observatories which are situated globally all over the globe. Some of them are in Chile, some of them in La Palma. We also do have a very good astronomical site in Ladakh, which we call it Hanle. There we have a 2-meter class optical telescope as well. So you can observe the stars or galaxies using these optical telescopes as well. And then you go on with higher energy. But as you know, and I believe that you have learned in this particular school, that most of the electromagnetic spectrum cannot penetrate our atmosphere. We have only two windows. One is in optical wavelengths and other one is in radio. I remember Professor Ojha discussed this in very detail to you. Now, I will not go into that much detail, but what I am trying to say that if you want to observe sources which are emitting from ultraviolet to gamma rays, you have to fly your telescope in this space to observe them. So to observe a source in UV or ultraviolet, you have to actually go to in space. And right now, India is having a telescope called UVIP on Astrosat, onboard Astrosat, and that UVOT can actually observe sources in UV regime. And then we have X-ray telescopes such as Astrosat, we have Chandra, we have NewStar, and so on. So many of them, Swift. And finally, at the gamma ray energies, we have one telescope which is launched by NASA. It's called Fermi-LAT. Fermi-LAT detects sources above 100 MeV to several hundreds of GeV. So I would start say 10 to the power 6 electron volt to 10 raised to the power 9 electron volts. And let's say if you want to go much higher in the energy regime, let's say you want to observe a photon which is emitting energies at 1 TeV or 1 tera electron volt, then you have to use some of these ground-based facilities which are called atmospheric Cherenkov telescope. And these facilities are basically an optical telescope with a very fast detectors. And I will try to explain this particular technique. And using this particular technique, you can actually detect the primary gamma rays and try to understand their energy, try to understand their spectrum as well as the direction by which they are incident on Earth. All right. So I'm mostly covering the Fermi-LAT and the other atmospheric Cherenkov telescope techniques and the physics behind it. Now, so as I already explained you that I'm
Excuse me, sir. The slides are not changing. It's stuck in the very first one.
okay. Is it changed now? No.
No, sir.
Okay, I think I can. Okay, give me a minute. I will try to. Hello, can you hear me now?
Yes,
Yes, sir, you're
yes,
audible.
Amit. Yes, Amit, go ahead.
Okay, thanks. I think there is some issue with WebEx or internet. I'll just come back in 1 minute to reshare.
Okay, sir.
Can you hear me now?
Yes, sir.
Yes, Amit. Yes, Amit, go ahead.
Okay, thank you. I'll just keep my video switched off. I think it could save some bandwidth. Yeah, can you see the screen now?
Yes, yes, Amit. Can you change the slide? Change a couple of slides so we know we can. Okay, can you go to the next slide? Yeah,
Yes,
okay, okay, we
absolutely.
can see it change. Okay,
Yeah.
fine, go ahead. Yeah.
Yeah, so already I have discussed this slide, basically telling you about different type of observations and different type of telescopes. So now I will come to the astroparticle part or the gamma ray astronomy part. So first of all, we have to understand a bit of history about gamma ray astronomy, how gamma ray astronomy started or come into the place, why people have bothered about gamma ray astronomy when we do have optical astronomy and radio astronomy, which are almost there from, optical astronomy is there from almost 200 years, or definitely more than 100 years, and radio astronomy also started quite long back. Why we need a very new field or new window in which we would like to observe, and this particular field started with the uh, sort of aim to understand the cosmic rays. So initially in 1912, Victor Hess actually observed or detected some of the particles which are isotropically coming or incidenting on our Earth without any change with the day or night. So basically, these particles were just bombarding our Earth atmosphere without any fail, and they are isotropic, they are not changing their flux with the time or with the seasons. However, they have seen some modulation with the seasons, but more or less they were constant, and it was believed that time that these cosmic rays are originated much far away in the universe apart from our solar system. So it was considered that they are not, initially it was not very clear, but over the time, over the several years, it was believed that these particles were originating much far away and not from our solar system. However, now we know that some of these cosmic rays also originate from the sun. However, the majority of them are originating from outside of our solar system, and most of these cosmic rays, around 85% of them are protons. The rest 12% is around is helium or alpha particles, basically helium nuclei or alpha particle, and rest 3% is the higher elements. So why this gamma ray astronomy started? Basically to learn the origin of these cosmic rays. And the origin of cosmic ray can be studied through several ways. Either directly try to understand or track these particles. However, it is very difficult as these particles are positively charged, they interact with the magnetic field of the universe and they lose their directionality. So you will never know whether if you track down towards the direction of incident of a particle, you may be totally wrong. And that is already shown in the figure that you can see the proton can gyrate and lose their directional information. However, that is not the case with the gamma rays, as they does not interact with the magnetic field and they can travel directly from the source to the earth. So they will not change their directionality. However, as they are photons, they can interact with the uh, other photons, let's say infrared photons, which are present throughout our universe, and they can actually produce pairs. So they also have some sort of horizon. So if a gamma ray starts very far away from us, then there is a great chance that it can interact with the some of these infrared background light photons, which are mostly in the infrared band, and they produce pairs. So those very far away gamma rays, which started very far away from us, will not reach us anytime. So gamma ray is a good way to learn or understand the cosmic rays. However, that also have a some sort of limitations. Then there is another possibility that we can also study neutrinos, and neutrinos do not interact much with the matter, so they can actually travel much farther distances than gamma rays, and they will not also interact with the magnetic field, so they will not lose any directionality. So if a source emit a neutrino, you can actually observe them using some of these neutrino detectors, and one of the neutrino detectors is IceCube, which is situated at the South Pole. However, as I already said, neutrino doesn't interact with the matter. It is extremely difficult to build a detector. So you require a very huge volume of the volume to actually make a detector which can significantly detect the neutrinos. And in this particular figure, I have also shown energy bands in which these observations can be made. So you can see for neutrino, there is a window is quite large. You can see that scale is given in log scale, and it is telling that roughly 10 raised to the power 10 electron volt neutrino 2, it can go to 10 raised power 22. However, for the gamma rays, we can only observe 10 raised power 10 to 10 raised power 14 electron volt gamma rays. And for protons, it's very small, 10 raised power 18 to 10 raised power 20. And why it is so? Because lower energy proton will be deflected more with the magnetic field, and you will never able to trace the actual direction of the source. And the proton more than energy 10 raised power 20 will actually interact with the other kind of photons or other kind of backgrounds, and there is something called ZZK cutoff. You will never able to observe some of the very high energetic protons. So you have a very small window to study protons. So the best window which we can use to understand cosmic rays are gamma rays. And here in the right side, I have two images. One is the image of magic twin telescopes, and the second image or a plot is basically telling us how the cosmic ray spectrum is, and basically tells you that if you look for the cosmic ray particle of energy 10 raised power 11 electron volt, what you will see actually, you will within a 1 meter square area, within 1 second you get one particle. However, if you go to 10 raised power 15 or 16 electron volt energy particle, if you want to look for that kind of particle in 1 meter square area, you have to wait for 1 year to detect one photon. And if you want to go much beyond the 10 raised power 18 or 19 electron volt, then even you require a 1 kilometer square area to detect one photon in one proton or one of that kind of particle, cosmic ray particle. You have to wait for 1 year. So now you can understand the numbers are falling very rapidly. Basically, they follow a power law. Initially, this power law have a power law index of 2.7, which actually get steepens at the around 10 to the power 15, which we call it knee region, where it reaches around 3. This power law index reaches to 3, and finally it again flattens up little bit at the ankle. However, it is not very clear why this change happens. So uh, in short, basically, if we want to study these particles and how these particles are accelerated, where they have been originated, the best option is to use the gamma ray astronomy, and that is why we are interested in gamma ray astronomy through space as well as ground-based instruments. And in next slides, I will try to cover some of these things. Okay. So how to detect a photon? There are several ways how to detect high energy photons. You can use a photoelectric effect, you can do the Compton scattering or a pair production. And we are using some of these techniques to detect the gamma ray photons. Now, here I have an image of a Fermi-Lat telescope. Fermi-Lat is a pair production telescope. Basically, when a gamma ray incident on the detector, it produces a electron positron pair, which is basically tracked by a silicon strip detectors. And finally, we using this silicon strip, the information from the silicon strip detectors, we construct the direction of the primary gamma ray. And at the base of the detector, we have a cesium telluride crystal calorimeter, where these two electron and positron pair deposit their energies, and that will give us the total energy of the primary gamma rays. And to avoid the cosmic ray going inside the detector, we have an anti-coincident shield, which we call it ACD. This anti-coincident shield basically works in the if this particular shield is triggered, then we will not consider that as an event. So it's basically the event should either be in the detector or in the this particular anti-coincident shield. And considering this veto detector, we call it veto detector. If in we have a event in this shield, ACD shield, then we will not consider that as a gamma ray event. It's a cosmic ray event. And using this particular technique, we try to construct the direction as well as the energy of the primary gamma ray, which is incident on the Fermi-Lab telescope. Fermi-Lab telescope, at the given time, it covers around 20% of sky, and it generally covers entire sky in 3 hours. It's in survey mode all the time. Most of the time it covers observe the sources in survey mode, but time to time it also steers sources like a telescope. And there are it can detect photons above 30 MeV up to 300 GeVs. However, sometimes we also detect higher energy photons, which are like up to 900 GeV. But those photons are rare because the high energy photons actually just pass through the detector and it does not interact with the your silicon so it does not interact with the your detector, basically a tungsten foil where it has to produce the pairs. So it also, but time to time we also get some of these bright some of these very high energy photons. However, the threshold is around 300 GeV. Now, here is the sketch of the Fermi-Lab. So you can see it has a column kind of thing which has a silicon strip detector. When a gamma ray incident on it, the gamma ray produces a paired electron and positron, and that electron positron pairs goes downwards and deposits its all energy into calorimeter. And this silicon strip detectors actually tell us the position of these interaction of electron positrons, and if you know the positions, you can reconstruct the direction of the primary gamma ray. Initially you construct all the direction of the electron and positron, and considering that direction, you using some of the mathematics, you can actually compute the direction of the primary gamma ray, and total energy can be counted at the calorimeter. Now there is so you can see the actual images and the sketches. Now this is another image where I have shown the image of a tracker where silicon strip detectors are uh, uh, put together, and you can see a gamma ray is coming and then interacting with the tungsten file and producing a pair which is traced by the SSDs or silicon strip detector, and finally depositing the energy to the calorimeter. On the left side, I have shown one of these calorimeter crystal. So it is basically wrapped. So if a photon interact in this particular calorimeter, all the energy is stored within this particular crystal, and using that information we can count how much energy main primary gamma ray has. Now if I go to outside in night time during these days, today is I think new moon, so you will see sky in optical. However, when you see a sky in optical, what you see basically some of the stars. We do not see much of the galaxy using naked eye, but you can, using some of the small telescopes, even you can see the Andromeda. And if you have very good binocular, you can see the Andromeda. And here on the left side of my slide, I have actually put one of the images which we call it Hubble Deep Field. This is an image taken by Hubble telescope in optical band for a very small window of the universe where it has observed millions of the galaxies. So this is how sky looks in optical wavelengths. However, if on the contrast, if I observe universe with the gamma ray telescope, so how it will look like. So on the right side there is a sky map shown by Fermi telescope. So this is how a gamma ray sky will look like. So you will see a very bright emission which is shown in red at the center part of this oval, which is actually our galaxy, or we call it a galactic plane. So there are several sources, mostly pulsars and supernovae lying in this particular lane. And then you will also see there are some of the sources at the top and bottom of this particular line, and what you see, these are the point kind of sources, and these are the extragalactic sources, mostly active galactic nuclei. And you will also see a structure very at the center part of this particular sky map, and these structures are called Fermi bubble. So basically, these are the some sort of remnant from our own galaxy, so which are emitting so remnant clouds. You can say these are the remnant clouds from our own galaxy, which are emitting in Fermi energies or in gamma rays. It is believed that it but we are not sure, but it is believed that these clouds are basically a failed jet. And you can also try to look this particular map very closely. You may perceive that this is a 3D image. So you can see the galactic plane is actually towards much closer to us, and there is some sort of projection made by NASA. However, it is sometimes difficult to perceive, but some people actually can perceive that this is a 3D image. Until now, Fermi has detected almost more than 5,000 sources, known sources. So Fermi has detected almost 9,000 sources, but for the 5,000 sources, we know the class and the type of sources. Almost for 3,500 sources, we are still not sure whether they are a blazar kind or Aegean kind of sources or pulsar kind of sources or what they are. So we are still working on those kind of sources. However, almost for 5,000 sources, we know that what kind of sources they could be. Now, the next slide is basically telling us about the sources, which I've already told very briefly. There are sources which we call it active galactic nuclei. These are the galaxies which host a supermassive black hole at their center. And some of these active galaxies used to have jets. Basically, a plasma is coming out very close to the black hole, perpendicular to the accretion disk or a plane of the galaxy. And these jets can accelerate particles up to very high energies, and within these jets, when particles are accelerated, they can emit gamma rays. And using Fermi telescope, we can observe these jets, and you can see these small dots in the sky map, and these most of the small dots above the galactic plane are extragalactic sources, which could be active galactic nuclei. Now, if you see the second image, the right side where I have written pulsar are mostly lying in the galactic plane. There are few of them are away from the galactic plane, but most of them are lie in galactic plane. Then there is a third kind of sources which I have already discussed, diffuse sources, and these diffuse sources, one of them, the diffuse sources Fermi bubble, which we have discovered by the Fermi, that it could be a remnant of a failed jet from our own galaxy. And very recently, few years back, Fermi, not Fermi LAT, but Fermi telescope also have another detector which we call GBM, has detected emission from the emission from the counterpart of gravitational wave event. So it's a first electromagnetic counterpart was detected from a gravitational wave event, and in MEV energies, and that was done first time by Fermi GBM telescope. Now, so I have already discussed about the Fermi LAT. Now you can simply ask, once we have a Fermi LAT telescope, whether why we need a different kind of telescope, or why we need a different kind of a gamma ray telescope. So what happens actually in space, we uh, cannot send a very big telescope. So there is a constraint or limitation for the size, and sending very heavy telescope in the space is another very difficult task, because for every kilogram weight we have to pay enormous amount. So to send a very huge detector in this space is very difficult. And as I already told, that for very high energy particles, either gamma ray or any particle, it requires an interaction cross section or interaction depth. So once you can have a 1 meter length detector, and using that particular detector, you can there is a possibility that, let's say, 300 GeV photon may interact within this particular length or a given volume. However, if I have a 900 GeV photon, there is a great possibility that this particular photon will actually pass through, because its cross section of interaction will be less towards the detector, or towards the material which is used to detect that particular photon. So basically, Fermi LAT has a limit. It can very well detect photons which are having energy up to 300 GeV. But above 300 GeV, most of the photon, not all, but most of the photon just pass through and they are not detected with the Fermi-Lab telescope. So if, let's say we want to extend our energy regime, what we can do, basically we can use some of the other techniques and use atmosphere as a detector. And this particular technique is called atmospheric Cherenkov telescope or atmospheric Cherenkov technique. And so at present there are four of them are working. There are four different collaborations. They call Magic, Fact, Hess, and Veritas. And so they are two of them, Magic and Hess, are situated at La Palma, Spain. It's a European collaboration. Then Veritas is a US or American collaboration, US and European collaboration, and Hess is also a European collaboration. But the telescope is situated in southern hemisphere in Namibia, to mostly to study galactic plane objects, mostly the galactic center and the sources, the galactic sources. And now what we are doing in India, we also do have a gamma ray or atmospheric Cherenkov telescope. So we have an observatory called HIGRO. It has two phases. The first phase was Hagar, which is a telescope built by Tata Institute of Fundamental Research, Indian Institute of Astrophysics, Bangalore, Saha Institute. And you can see that particular telescope in this particular figure. So there are 7 of them. So they are a small telescope. They observe the Cherenkov light, which I will explain what exactly it is. And this particular telescope is situated in Hanle, Ladakh. And the next phase of this particular HIGRO observatory, we are actually building a telescope of 21 meter diameter. So which is already completed and will be commissioned in next few months. So now you can think about the difference in the length scale. The Hagar is having a 3 meter diameter, and the MACE is having a 21 meter diameter telescope, and it will be the second largest telescope of this kind. So the largest one is Hess telescope, which is 27 meter telescope. Now this will be a 21 meter telescope and very much like Magic kind of telescope. Okay, so now now I will try to explain that how we will detect the very high energy gamma rays using this particular telescope or this technique. And this is situated in India, in Ladakh region, and the place is called Hanle. Okay, so there are two more telescopes which I am associated with right now. One is called FACT, another one is called called Magic. Both are situated in La Palma Island. The difference between these two telescopes are, one of them is very small, which is called FACT. It's only a 3 meter diameter telescope. However, 3.9 meter diameter. However, the Magic is around 17 meter diameter telescope. It's very big. And both have a different type of detector. So what you have in the basket, basically a focusing optical telescope, and on the focus you have a detector which detect the Cherenkov photons. FACT is using the GAPDs or silicon photomultipliers. However, Magic uses the photomultiplier tubes. What is the difference? Basically, FACT uses diodes, and these diodes can also operate in high background. However, Magic uses the photomultiplier tubes, and these photomultiplier tubes cannot operate in high background. It means once the moon rises, the background increases, and Magic has to stop the observations because PMT cannot handle very high background. However, on the other hand, FACT can handle or GPDs can handle the high background and they can still observe. So FACT has a very different kind of a detector and Magic has a different kind of a detector. There are advantages and disadvantages of both. However, technology wise, making FACT like detector is very complex, and but it allows you to observe throughout the observation window. So we do not care about the moon. Even with the full moon we can observe and detect gamma rays. However, that cannot be done either with Magic, Hess, or Veritas, or not even MACE. So that is the advantage using the FACT telescope. However, it is small, so it requires more time to observe the same source of the same strength. Now, here I have shown you some of these pictures of magic telescope, the magic camera, or which we call it detector on the right corner, and then some of the photomultiplier tubes. So these kind of detectors are used, not exactly same, but similar kind of detectors are used to build the camera or the detector which is mounted on the focus of a magic telescope. What is mounted on the FACT? So you can see there is a small diode pin is shown in the left side. So these kind of small detectors are used to make the FACT camera or FACT detector, and there are 1440 small GAPDs are used to build the detector for FACT camera. And using this particular detector, we can even observe during the very bright moonlit nights also. You can also see a very peculiar kind of Winston cone or the light concentrator. It's called Winston cones, and these Winston cones are glued on the detector or GAPDs to collect more light or basically focus light on the detector. And because if you put these GAPDs, there will be gaps between two particular GAPDs or dead area we call it. But using these Winston cone, we can avoid that area. So they can be joined or glued with two surfaces. So there will be no dead area in the camera. So you can basically utilize that this part of which is the dead area can be removed using this technology, which we call the Winston cones. Now, actually, what happens once we have a primary gamma ray or a cosmic ray, anything? It could be a proton or it could be a gamma ray. They can be started from the, let's say, from a supernova. Let's say Crab Nebula. From Crab Nebula, there is a gamma ray originated and reached to the Earth atmosphere. Once it reaches to Earth atmosphere, it interacts with the either oxygen or nitrogen nuclei and produces a shower of particles. If it is a gamma ray, then it creates a electromagnetic cascade where uh, electron and positrons are created, and then further this shower develops. I just want to know whether I am audible to everyone.
Yes, sir, you're audible.
Okay, fine, thanks. Yeah. So, and in case of the protons, once proton comes to the at the top of the Earth atmosphere, it also interacts with the your nitrogen or oxygen nuclei, and it can produce a hydronic cascades. So, how these cascades are different, I will try to explain. So, let's see. I have a gamma ray photon. It comes, interacts at the top of the atmosphere with one of these molecules or nuclei, produces electron and positron. Now, these electron and positron still have a lot of energy. So and they also have a downward momentum. So they starts moving towards Earth or the ground. However, when they travel, they radiate through Bremsstrahlung radiation and again emit even lesser energy gamma rays. However, if the lesser energy gamma rays, which is emitted in the second round, even have a more energy than the pair production energy, then again this gamma ray will produce a pair of electron of positron, and these electron positron pairs again go downwards and produce other low energy gamma rays through Bremsstrahlung, and this chain goes until the entire shower loses its energy. I will not go into the detail, but at some point, particles will not have enough energy to produce Bremsstrahlung, so there will be no gamma ray radiation. However, in this process, there will be a particle shower is generated. So you have a lot of electron positrons which are moving towards Earth with a very high speed, almost the speed of the light. And the very similar concept happens in the hadronic shower. But in place of only electron positron, we also get pions. So proton comes and interact with the atmospheric nuclei, produces pions, pi naught, pi plus and pi minus. Pi naught again decays into gamma rays, producing electromagnetic cascade, plus you have pions, and they produces a lot of muons, kaons, and several other particles. So now these two showers actually coming down towards Earth with some linear momentum. On the right side, there are two images are shown that how this shower develops. This is a simulation done using Corsica algorithm or Corsica tool. So you can see the lateral as well as elongated view. So at the ground, you can see that for the gamma rays, you get a very circular image. However, for the protons, it's a very diffuse image. And even for the lateral view also, you can see gamma rays are very compact. However, protons are very scattered. So these are the main properties, and these properties are used actually to segregate between gamma ray event and hadronic event. Now, when this particle or this shower moves with the almost speed of the light in the atmosphere, you also know that nothing can move faster than the speed of light. However, this particular statement is not true if particles are moving in the dielectric. So our atmosphere behave as a dielectric, and the particles, these particles which are created in the showers, they actually move much faster than the speed of light in the medium. So let's say if you are in the water, you're almost 3/4 speed is reduced. So the speed of light is almost 3/4. However, the particle can still go with the speed of 0.99, 99% or 99.99%. So once the particle moves much faster than the speed of light in the medium, they produce a radiation called Cherenkov radiation. This is a bluish radiation, mostly fall in the ultra violet to blue region. So what exactly happens once a particle which has having lesser speed than the speed of light in the particular medium, and it passes through the medium, it creates basically it disturbs the dielectric and create a electric field. So basically pushes the molecules to away from the point where it is at the current position, and produces a dipole. However, when this particle moves with lesser speed than the speed of light in the dielectric, it creates a very symmetric disturbance. Also, all the dipoles are very symmetric. So once this particle is passes, because everything is symmetric, it comes back to the original configuration, and no emission has been emitted or no radiation has been emitted. However, in the case of the other case, when the speed of light is lesser than the speed of particle, this configuration get asymmetry in azimuthal angles. In the y direction. So there is a due to asymmetry when particle passes from the dielectric, the entire system has to come back to the previous state, and to do that they have to emit the radiation, and that radiation is called Cherenkov radiation. I will try to explain in next slide as well with much more easy way. So let's say you can see the three figures. So first figure is you can see the gray one. You have electron and a photon. Both are traveling almost with the 99.99 percent of the speed of light. So photon can travel with the c, but your electron is moving with the 99.99% of the c. So most of the time they are catching up. However, once this photons goes into the let's say water, at initially both were at the same place. However, now the speed of the light decreases by almost 3/4 in the water, but the particle, which is electron, actually does not reduce its velocity. So at some point it actually goes ahead to the light, ahead to the photon. And when this happens, and so let's say after some time, what happens, your electron will be much uh, ahead of the photon, which have actually started at the same point or same time in the water. Okay, once this happens, what exactly happens, as I explained, when a particle moves, it disturbs the molecular symmetry in the dielectric, sets up electromagnetic fields, But once it passes through, the dielectric has to come back to its original position, and to do that, it has to emit radiation, which is called Cherenkov radiation. What exactly happens? Okay, so mostly this Cherenkov radiation is coherent, and what exactly happens? So you can see the third column, where I have shown some of these photons, some of these events. So you can see, let's say at the first point, the top figure, at point X, an electron has emitted a wavefront or a photon. Now this wavefront will move with some speed c by n. However, the particle in the water will, or in any dielectric, will move almost with a 99% or 99.99% of the speed of light. So what happens, at some point this particle will actually cross the wavefront. Now at another point X, the second point, it will create another wavefront, and so on. And this particular particle will emit continuously, and and you can see these wavefronts will be growing. However, the interesting point is they will actually make an envelope kind of thing. So that's how the Cherenkov radiations are emitted. So all these wavefronts basically form combine. If you combine all of these spheres, then what you get is a wavefront, and these wavefronts are basically a Cherenkov radiation, which is emitted coherently. Now, what you can see, okay, these Cherenkov lights are actually only emitted for few nanoseconds, let's say 10 to 15 nanoseconds. So you have a particle which is having a lot of energy, which is moving much faster than the speed of light in the dielectric, and then it emits for, let's say, 5 to 10 nanosecond, and then it reduces its energy. And once it reduces the energy, it is not able to again reduce the Cherenkov light, because the speed has been now lesser than the speed of light in the dielectric. And so what you get is, only for 10 nanosecond you get a pulse of radiation, and that pulse of radiation is mostly in the UV and blue region. So this is how the Cherenkov light is emitted, and we, using these optical telescope and fast electronics, we at the ground we try to detect this particular effect or radiation. Now, mostly this Cherenkov light is emitted in a cone. And what exactly we do with the atmospheric Cherenkov technique? So as I already said, these particles are moving towards the Earth, which are created in the shower. And these showers actually create a Cherenkov light, which can be detected on the ground using optical telescope and a fast detector. Mostly the cone of Cherenkov light is of order of 100 meters. So if you put your telescope within this pool of optical light or blue light, you can detect the photons. Mostly on the detector, what you see is an elliptical kind of an image of a shower or of a Cherenkov photon. Sorry, you get a image of a shower which is producing Cherenkov light. Mostly it is oval for the gamma rays. However, it can varies with the shape of the image can vary with the different species. For the proton, it could be a different shape. And here there is a cartoon is shown that Crab Nebula is basically emitting a gamma ray, which interacts at the top of the atmosphere, produces a shower and a very faint bluish light, a Cherenkov light in a cone, which can be detected by Veritas telescope. The width of this particular Cherenkov light is almost 500 meters or so, or 10 to 15 nanosecond. It varies a bit, but 10 to 15 is a very decent number, 10 to 15 nanoseconds. Now, if you have such system, basically you can place this such system in a dark sky, and you turn your telescope towards some of the gamma ray emitting sources, and using the Cherenkov technique, basically the tertiary effect, you observe these images and do some mathematical calculation and try to understand their direction as well as their energy. Now, there are some differences. Now, you can ask me a question: how I know which one, which image is due to a proton, or which image is due to a gamma ray? So they have a very different photon distribution on the detector, or on the ground. So you can see here I have put some of these photon distributions at the ground. So you can see the gamma ray initiated shower produces a very symmetrical shapes, and however, in the case of proton initiated showers, they are very fuzzy. So they have so many, because they have more branches than electromagnetic showers. So if the shower is hadronic, it may also have electromagnetic branch. It will have a muonic branch. It have a some neutron related uh, neutral branch. So it can produce photons in much uh, larger area than the gamma ray photons. And gamma ray photons are very compact because they are coming from only one kind of species. It's electromagnetic cascade. So you can see the photon distribution, and using these methods, using measuring this particular distribution, we can segregate between a gamma ray and a photon. Now we can use a very same technique, basically to image them, and we can also use the timing information. If you place more than one telescope in a observational pool of Cherenkov light, if the shower is coming from the vertical, then basically all the telescope will be hit at the same time. However, if the shower is coming from an angle, then your first telescope will be hit first. The telescope which is in the direction of the shower will be hit first, and the telescope which is far away will be hit last, and there will be some time gap of few nanoseconds, and using that information also you can construct the direction of the gamma ray or a proton shower. Okay, so how these different images of different Cherenkov showers looks like on the camera plane? So you can see they could be very different kind. Here some of them are gamma rays. Let's say if you see, uh, um, I would say C2, sorry, C3, that looks like to be a proton shower because it's quite fuzzy. If you see E4, that is due to muon. It's a called muon ring. D5 is also protonic, and I would say gamma ray could be either C1 could be gamma ray, C3 could be a gamma ray. So basically, gamma ray images are mostly oval shaped. Now, how actually we do it? The analysis, it's very quite simple. You get these images, then you put a threshold. That okay, why you need a threshold? Uh, as I already said, we are using an optical telescope, so even night sky or stars can also trigger your telescope. However, these sky or night sky only trigger telescopes at least 1 or 2 pixels. So what we request from our telescope, that at least we have like 1440 pixels in our fact camera. So what we require, at least more than 10 pixels in given time window, let's say 10 nanosecond or 20 nanoseconds. This 10 pixels has to be triggered, or should be hot. Why? Because the Cherenkov light is coherent. It is emitted within 5 to 10 nanoseconds. So if a shower emitted a Cherenkov light which is in blue range, it will hit a detector within that 10 to 15 nanosecond, and it will hit more than 1 pixel. However, in case of a starlight or a night sky background, it mostly hit 1 or 2 pixels. So these are the trigger criterion we generally put uh, to distinguish between night sky and Cherenkov event. Now, basically, then you do some analysis and you pull out these showers or images, which mostly look like oval shaped, and using one of the technique called Hillas parameter technique, we try to find out whether they are gamma rays or they are proton initiated showers or they are muon initiated showers. Finally, I will show you how the sky looks like in TV. I have shown you how it looks like in GeV energies with Fermi. With TV, you can see mostly we have extragalactic sources. However, we also do have a few pulsar wind nebulae known at TV energies. There are a lot more sources at galactic plane, which here we have shown in gray color, are actually not very, we do not know about them. So we know they are gamma ray emitting sources, but we do not have a classification of them, and where we believe the upcoming telescopes such as CTA will help us to distinguish and try to understand what kind of these sources, and they are called dark. So what is the standard candle for us? Every telescope has to actually test what exactly, whether our telescope is correct or not, whether it's giving the correct values or correct flux. So the Crab Nebula is a steady source which emit uh, uh, gamma rays at the constant rate, and we use Crab Nebula as a standard candle. Now, here how gamma rays emission can be, so how gamma ray can be originate, or how a gamma ray can originate in a astrophysical source. There are several possibilities. One of the possibility is that low energy photon can be hit by an electron. So an electron can hit and put a low energy electron to higher energies. It's called inverse Compton scattering. The other possibility is that a proton can interact with photon or ambient medium or a proton and produce pions, pi naught, and these pi naught decay into two gamma rays. So these are the other possibilities of creating gamma rays in astrophysical sources. Now, I have already discussed about the active galactic nuclei, and here are the pictures. So mostly we believe that most of the gamma rays are generated or originated from the active galactic nuclei jets, and some of these jets are actually directed towards Earth, and these kind of active galactic nuclei are known as or classified as blazars. And mostly Fermi and the atmospheric Cherenkov telescope try to observe some of these sources, which we call blazars. So this is a video which I do not know whether you can see it, but this is an image of a blazar, and emission can takes place very close to the black hole. And the black hole is surrounded by the accretion disk, and perpendicular to the accretion disk there are jets which are made of ultra relativistic particles, and a gamma ray emission can take place within these jets through either inverse Compton scattering, or if there are protons, then could be a proton photon interaction, and then a pion decay into two gamma rays. And finally, what kind of scientific problem we can approach with these kind of telescopes, either Fermi or atmospheric Cherenkov telescope? So let's say if we want to know how these very active jets or jets of the active galactic nuclei are launched. So it is believed that these enormous jets, which are almost up to megaparsecs, can be launched due to the or can be powered through the rotational energy of a black hole. So EST has very recently proposed this using using MAT7 observation, and they have made a video, or basically it's a simulation that jet rotational energy is actually lightening up the jet. So you can see the particular simulation. This is in radio wavelengths. However, a very similar things can also be set for the gamma ray energies. That gamma ray emission can also be, or a very similar simulation can also be made for gamma rays. So this particular simulation consider a Blanford-Znach process where the rotational energy is launching the jet from an active galactic nuclei. And very recently, so already EST telescope or Event Horizon telescope have observed MAT7 telescope and its shadow, and shown that this is the one of the possibilities that Blanford-Znach process can launch the jet. And however, they still were not very sure about it, and then they observed some other sources. In gamma ray energies, what exactly we observe, basically we try to observe how the flux changes with the time, and some of these fast variabilities actually tell us lot more information about the jet launching or the jet content. And several atmospheric Cherenkov telescopes such as HESS and MAGIC and the Fermi Lab telescope has detected very fast variabilities. The variabilities of the order of few minutes. When I say variability, it means the flux. If you observe a source over the time, how much time a source takes from one state to go to another flaring state or higher flux state. And let's say the counts are 10 at current time, and after 15 minutes the counts become 40. So this is basically change of almost 4 times, and this kind of changes can actually tell us the size of emission region in the blazar. And using this particular information, we have discovered several telescope ACTs and Fermi-Lat has discovered that the most of the emission in the black hole comes very close to the black hole. And last year, we have detected some of the very interesting patterns in one of the blazar, which is called 3C279. Till now, nobody was known how these jets were launched, but it was proposed that using Blandford-Naik process, these can be launched. And Blandford-Naik process uh, predict a certain kind of pattern in the light curve at the gamma ray energies. However, Blandford-Naik has proposed this in 1980s, and till 40 years, this kind of particular pattern was not discovered. Only last year, 2018, first time Fermi-Lat telescope has discovered that pattern, where there is a slow variation, and on top of that, very fast flares, which the source varies within few minutes. Like within 3 minutes, the flux become almost more than double. And this kind of pattern actually tell us that emission is or the particles are actually accelerating through magnetic reconnection, and which is a prediction of a Blandford-Naik process. So we have discovered this in last year and published in a very reputed journal. Finally, this work is done with my collaborator, Professor Manham, and it agrees with very well agrees with the Event Horizon Telescope observations of 3C279. And finally, we have made a statement that now we know where the emission actually takes place in the where the gamma ray emission takes place in the 3C279. So using Fermi-Lat or atmospheric Cherenkov telescopes, we can make a very significant study and research related to the jet physics. And you can see this is a cartoon where a black hole is rotating and launching a very steady jet. Finally, I simply tell us what is the future. In future, we are going to build a telescope which is called Cherenkov Telescope Array. This is a global consortium where India is also a part, and we are trying to develop some of these detectors, some of these small telescopes, and some more subsystems of the Cherenkov Telescope Array. Thank you very much for this lecture. You can write to me if you have any questions. I can take some of them here. You can write to me on my email address. Also, if you want some of these new discoveries or scientific information, time to time I post it on my Twitter handle, which is Amit008 underscore Shukla. So you can also follow my Twitter handle for some of the very interesting new scientific research. Thank you very much.
Thank you, Amit, for a great talk. We're open for questions. In fact, there is one question from Priyankar Mukherjee already. Maybe I can just read it out for you.
Yes, that would be great.
Okay. So Priyanka says, in one of your slides on the tracker device made of silicon, you showed that the gamma ray has to travel a certain distance through the device before it splits into an electron and a positron. Does this distance depend on the initial energy of the gamma ray?
Yes. So basically, for Priyanka, definitely I can say in upcoming classes, I'm going to teach this particular concept where we call the interaction depth. So this interaction depth depends upon the energy and the cross section, and that varies with the direction and the material and the energy of the primary.
Any further questions for Amit?
Can I ask one?
Sure, go ahead.
So, firstly, thanks for the lecture. I just wanted to know how do we actually get any kind of astrophysical information about the source from the Cherenkov radiation caused by high energy gamma rays? I mean, we are not directly detecting the gamma rays that may be originated at some astrophysical source. Rather, we are detecting the radiation by some other high energy particles that are produced by interaction of, say, gamma ray photons and atmosphere. So in this scenario, do we lose any information that we could have obtained by directly detecting the gamma ray photons?
Yes. So once you have this tertiary effect, your direction construction of the direction is very difficult. That is the one of the challenges. Now, as I said, this particular Cherenkov wavefront only lasts for 15 nanoseconds. So we have to use the very fast electronics, which actually has to distinguish between photons which are detected could be only separated by 10 nanoseconds or 5 nanoseconds, or even what actually we do, we go to pico nanoseconds. So once you do that, how precisely you measure, how precisely you can actually construct the direction. So what we lose is the direction. So that is why I could not cover the angular resolution of the gamma ray telescopes are not as good as optical telescopes. So if I have shown you very beautiful image of Crab Nebula, right? So you can see the crab and all these structures in the Crab Nebula. However, if I observe with the gamma ray telescope, either with LAT or with MAGIC, what I mostly see a very bright spot and no structure. So what actually we lose the angular resolution, which is one of the things. But however, you cannot even get it with the Fermi as well. But with the effect of the secondary and tertiary effects, you lose a lot of information related to direction. So your
Okay,
errors
sir.
are much larger.
Okay, sir. Thank you. Thanks a lot.
Yeah.
Any other questions for Amit? All right. I don't see any other questions. So let's thank Dr. Amit Shukla again. Thank you very much, Amit,
Thank you,
for a
Siddharth.
great. Thank you. Professor Sen Gupta, welcome.
Yeah, can you hear me?
Yes, yes, I can hear you. Do you want to share your slides? And in the meantime, I can introduce you.
Yes.
Thank you.
See my slide?
Yes, sir. Yes, sir. I can. All right. It's great to have with us Professor Sujan Sen Gupta. Professor Sen Gupta did his BSc in mathematics from Bakura Christian College in West Bengal in 1987, MSc in mathematics from Burdwan University in 1989, and his PhD in physics from the Indian Institute of Astrophysics, Bangalore, in 1996. Professor Sengupta's interests are extrasolar planets, the theory and observation of extrasolar planets, and the atmosphere of brown dwarfs and extrasolar planets. So, welcome, Professor Sengupta. Please go ahead.
Good afternoon, everybody. Please fasten your seatbelt. We are going to the space.
Space, the final frontier. These are the voyages of Starship Enterprise. Its continuing mission to explore strange new worlds, to seek out new life and new civilizations, to boldly go where no one has gone before.
So to explore strange new worlds, to seek out new civilizations. But that's the science fiction. And today I'm going to tell you the systematic and scientific effort by astrophysicists with the aim to answer the eternal question of mankind. Is anybody out there? Thank you, the organizer, for your kind invitation, and for, in particular, for Oviru for the communication. So we know one planet very well. That's the habitating planet where we live, where we do all our daily work, where we survive. Now, about 5,000 years ago, the Sumerian, they believed that their civilization, their technology, their agricultural procedure, all are taught to them by intelligent life from outer space, outside the earth. At the same time, the Babylonian thought that the millions of light in the night sky, which was not known at that time as stars or planets, so they were the resident of the god and goddesses. The ancient Greek also believed that the moon is the place for the departed soul and the god and the goddess. But then, about 300 BC, Aristotle put his theory that Earth is the center of the world and it's a special place. About 200 years after Jesus Christ was born, there was again the support by Ptolemy about this geocentric universe. Now the Catholic Church gave a dictation that nobody should oppose about this model, and then for 2000 years people were forced to believe on the geocentric world. But as more and more observations started coming, and then it was quite apparent that this geocentric concept is contradicting the observation, the motion of the planet. And finally, in 1500 AD, that is after 2000, almost 2000 years, Kepler came out with, Copernicus came out with his heliocentric concept of the world. But Copernicus thought that the sun is the center of the whole universe. Not only the planets, but also the stars are also orbiting the sun. This concept was supported by Giordano Bruno, but this was directly against the Catholic Church, and Bruno was killed, was burned alive. The same, a similar fate, you know, about Galileo. But Giordano Bruno was the first who realized that if the lights, the thousands of millions of lights in the night skies are very similar to the sun, then they should have also planetary objects or planets around them, or they should have also planetary world around them. And if that is the case, if those lights are having planetary system, then some of the planets definitely be very similar to the Earth. And if there are such type of planet which are very similar to Earth, then somewhere there may be life. And so people at that time started thinking about the planet outside the solar system and life, although this imagination of extraterrestrial life or extraterrestrial intelligence is very ancient. So the search started, but at that time, after 1500, after Copernicus or Kepler or Galileo, those astronomers was busy in discovering the more and more solar planets. The first confirm, the first report, the scientific report of a planet outside the solar system came from Madras Observatory in India. This Madras Observatory was established in 1786 by the British East India company for the meteorological purposes, but then the people who are working, they use it for astronomical purposes. So during 1855, the then director of this Madras Observatory, Captain William Stephen Jacob, by monitoring, by taking photographic image of a binary star system 70 Ophiuchi, found out that this binary system, there are two stars, they are not following Kepler's law. So he then somewhat hypothesized that if there is a Jupiter-sized planet in this system, then this anomaly in the motion of these two stars, the binary star, can be explained. Incidentally, this Madras Observatory is the origin of the the present Indian Institute of Astrophysics, where I have been working. So this Madras Observatory was shifted to Kodaikanal Observatory in 1899, and in 1971 the headquarters in Bangalore was established. In any case, after Captain William Stephen Jacob reported his hypothesis or his explanation of the anomaly in 70 Ophiuchi in monthly notice of Royal Astronomical Society, a few observers also came out in his support. For 50 years, it was believed that 70 Ophiuchi may have a Jupiter-sized planet. But as the technology improved, as the observation improved, it was later on found that Captain Jacob made a mistake. He has made an overestimation by removing the air, by not considering the atmospheric effort of the Earth. Nevertheless, this report is considered even by NASA and by the European space agencies as the first false alarm for exoplanets. After that, for nearly 100 years, more than 100 years, people started searching by using mainly the photographic plate for planets, for worlds beyond our own. Then finally, in 1995, this gentleman, Professor Michel Mayor, reported, and his student Didier Queloz, reported the first confirmed discovery of a extrasolar planet around a star, around a sun type of star that is named 51 Pegasi, and the planet is named as 51 Pegasi b, which is slightly bigger, which is very similar to our Jupiter in the constellation of Pegasi. So now, if you see by a small telescope, by an ordinary telescope, this 51 Pegasi b is a very nearby star, but we know that the planets don't have their own light, and they are hidden, even if they are bright by reflecting their starlight, they are hidden by the intense brightness of their star. And therefore, these planets cannot be seen, or they cannot be observed directly because of the intense luminosity of the brightness of their star. So the astronomers take indirect method to detect or to discover these worlds beyond our own world, to detect the planets orbiting around stars other than the sun. The method that Michel Mayor and Didier Queloz used is called the radial velocity or Doppler method, which was proposed by Professor Otto Struve in the journal Observatory in October 1952. So imagine that after almost 45 years, this method was successfully employed to discover the first extrasolar planet. Now, what is this radial velocity or Doppler method? Now, when two stars or two celestial objects orbit around each other, for example, a binary star of equal mass, they don't orbit around anybody's any of the body's center, but they orbit around a point which is called the barycenter. So if the two objects have equal mass, then this barycenter lies exactly in the middle of the line joining the center of the two objects. But if one of the object is heavier, then this barycenter moves towards those heavier object. Like that, if there is a planet orbiting a star, then this barycenter or the center of rotation goes inside the star, but not exactly overlaps with the center of the star. As a consequence, it causes a wobble in the star. Now, if you observe this object edge on, then you will find there is a radial velocity, to and fro radial velocity in the star. Now, we know that our Jupiter impart a radial velocity of 12.4 meter per second, and the Earth also imparts a radial velocity, a tiny radial velocity at 10 centimeter per second to the Sun. So the astronomers detect this radial velocity by using this method to confirm the presence of the planet. But how they detect this tiny motion, this tiny radial velocity? So they send the light to of the star to a instrument called spectrograph. Now I think all of you know it, which splits the light, and when it splits and the detector produces the spectrum of the star, you get a few dark vertical lines in the spectrum, which are due to the absorption of the starlight by the material atoms, namely the atoms present in the outer layer of the star, that is called the atmosphere of the star. Now, if the star is static, then these lines, this vertical line of the absorption line, are fixed corresponding to a specific wavelength. Now, if the if the stars have motion, then these lines, they move systematically. When the star moves towards you, there is a blue shift in the light, and if it moves away from you, this is there is a red shift, and accordingly this line also moves periodically. So by noting this tiny movement of this absorption line, in particular say iodine line in the case of Mayor and Michel, and now argon line is used, the astronomer confirmed the presence of a planet around the star. The next method is called the transit method, the second popular method. And this was also proposed by Professor Otto Struve in the same issue of the journal Observatory. What is this transit method? That when a planet passes across the stellar disk, then it reduces, although very tiny amount of light from the star. So as the planet transit across the star, you can see that there is a drop in the brightness of the star, and this drop is very systematic and very periodic. If there are more than one planet transiting across the star, then this light curve, this drop in the brightness, is also modulated. So by using this transit method, or by monitoring the reduction or the decrease in the brightness of the star, the planet can be confirmed. Not only a planet can be confirmed, its size can also be determined, and its orbital inclination angle can also be determined. In IIA, we follow this transit photometry method by using Indian telescope in order to search for new planet, not only in search of new planet, but also to follow up the already discovered planet by using the Jagadish Chandra, the 1.5 meter, 3 meter Jagadish Chandra Bhattacharya telescope at Bhainubappa Observatory in Kavalur, as well as the Himalayan 2 meter class Himalayan Chandra telescope and in Indian Astronomical Observatory in Hanle. And by using this telescope and by using a state-of-the-art, our own developed computer code that reduces the noises and then model it, we also find out various parameters of the planet already discovered. We improve the parameters, and our observation, because we use a larger aperture telescope, and our analysis method is so precious that we can update with very high accuracy of the physical properties of the planet. So far we have done for 10 planets, and our data is so precise that it has been included as the default value in NASA's exoplanet archive. So this is considered by NASA as the best value that our two telescope and our analysis has detected. Nevertheless, before 1995, we knew that we have we know only 9 planets in the solar system. We didn't know any planet outside the solar system. In 2006, the International Astronomical Union, that is the Senate or the Parliament for the astronomers, they resolved that Pluto is no more a planet. That is because we thought that Pluto is a planet because we didn't know much about this planet Pluto before 1990 or even before 1970. So when we came to know more information about Pluto and the discovery of Pluto's satellite, that is Saturn, we found that Pluto is even lighter than the moon. And then the discovery after 1995, the discovery of several giant Jupiter type of planet introduces this controversy. And then subsequently in 2006 IIU meeting, it was resolved that Pluto is considered as a dwarf planet and not a contemporary planet. So during that time, after the first discovery by Mayor and Michel, there are quite a few planets was discovered immediately. And the number of planet has the number of new planets has increased enormously. But at that time, all the ground-based telescope was used. So this ground-based telescope has a capacity to search for new planet within 300 light year radius around the sun in our own galaxy. But then with the discovery of so many planets, NASA then came into the picture, and it decided to send a dedicated space telescope called Kepler. Kepler was launched in 2009, March 2007.
7, 6, 5, 4, 3, 2. Engine start. 1, 0, and liftoff of the Delta II rocket with Kepler on a search for planets in some way like our own.
Earlier engine chamber pressures are building. Groundlit solid motors are building in chamber pressure.
Fantastic. So as soon as Kepler was put into the orbit and it became functional, and we started getting data and we analyzed that, a large number of planets with the diverse properties has been discovered, and our the search region was extended to 3,000 light years, but in a narrow cone. But within even this narrow cone and within that 3,000 light years, we have discovered so many varieties of planets that our concept on planetary science, our concept on the planetary properties, our concept on the formation of the planet, everything got completely revolutionized. We know in the solar system, Jupiter is the largest and the heaviest planet, but Kepler discovered planets which are about 10 times heavier than Jupiter and about double the size of Jupiter. Jupiter, our Jupiter is far away from its star, the sun, and it is very cool. But then Kepler discovered some Jupiter-sized of planet which are very near to their star, and it is so near that their temperature is so high that even gold and iron can melt in their atmosphere, in their surface. At the same time, Kepler discovered planets which are intermediate between rocky planet and gaseous planet. These are called mini Neptune, which are not there in our solar system. Planets are discovered around binary star or multiple star system. Those are called circumbinary star. In fact, our nearest star, the Proxima Centauri, is actually a part of a three stellar system: Alpha Centauri A, Alpha Centauri B, and Proxima Centauri. So a planet is discovered around Proxima Centauri. So imagine that this planet's temperature, this planet's season, all are dictated not by one star but by three parents. Now these planets cannot be observed. They are very near to the star, so they cannot be observed directly. So these are all artist imagination. But very soon some planet has been discovered which are directly imaged, which are far away from their star, but they are so young that they are still very hot and they are emitting infrared radiation. And by blocking the starlight by using an instrument called coronagraph, the image can be taken of the star. Now these stars, these planets are all special planets. They are very giant planets and they are young planets. So all type of planets has been discovered. So consequently, the focus was shifted to those planets which can be habitable, which can habitate life, because the ultimate aim is to find out the answer to the eternal question, is anybody out there? So where to find out those type of planet which will be very similar to Earth, which can harbor life or which can be habitable. Now these are called, this region is called the circumstellar habitable zone. This term was first used by Su Wang in the journal Astronomical Society of Pacific in 1959. So a habitable zone is a region around a star where the temperature due to the star is such that water can exist in liquid form. So now imagine that there are somewhere in the corner of this galaxy, there are extraterrestrial intelligent, which are similarly curious to know whether life exists beyond their own system, but their civilization is quite old and much advanced. So they have much better telescope, much better computational system. So they are also searching for planets which are habitable. Now how they will find? So if they discover the sun, and if they consider only the luminosity or the brightness of the sun, and they discover all the planets in the solar system, they will find out that all the three planets, Venus, Earth, and Mars, are habitable, so that their temperature is appropriate for water to remain in liquid form. But all these planets, all these objects has a reflective property. So they reflect certain amount of starlight received to the space. For example, Earth reflects 30% of the sunlight into the space. The Mars, it reflects 20% of the sunlight into the space. And Venus, it reflects a whooping 70% of the sunlight to the space. Therefore, if this reflectivity or the albedo is considered, then the extraterrestrial intelligence will think that none of the planet in the solar system is habitable, because then the habitable zone has to be shifted much near to the sun to make them warm enough for water to exist in liquid state. But we know that on Earth, we have a habitable situation here. The temperature is such that water can exist in liquid form. In fact, water on Earth exists in all the three states: gas, solid, and liquid. So what this extraterrestrial intelligence will miss while detecting, while finding out that the Earth has a habitable atmosphere, that is called the greenhouse effect. So when the starlight enters, the sunlight enters to the Earth atmosphere, it heats the surface and it warms up the surface. Now this heat energy again goes back, it reflects back to the space, but with a lower energy. So energy gets reduced into from the optical to the infrared. Now this weak radiation, it gets scattered with the molecules in the atmosphere, with carbon dioxide, with water, with oxygen, with nitrogen, etc. And by getting several times scattered, it cannot escape into the space. It gets trapped into the atmosphere, thus increasing the temperature of the Earth atmosphere. So if this greenhouse effect was not there, the temperature, the mean temperature of the Earth would have been minus 15 degrees Celsius, but because of the greenhouse effect, the temperature increases to 30 degrees Celsius, and so the mean temperature of Earth become 15 degrees Celsius. The same time, Mars, it has a very thin atmosphere, so it doesn't have a effective greenhouse effect, and it is already far away from the sun, so it is much cooler. But on the contrary, Venus has a very thick atmosphere, and although it reflects 70% of the sunlight back, because of the thick atmosphere, it has undergone a runaway greenhouse effect, which has increased the temperature in such a way that the mean temperature of Venus is whooping 450 degrees Celsius. So minus 70 degrees, it would have been without greenhouse effect, but because of this greenhouse effect, its temperature is 450 degrees Celsius, thus making Venus the hottest planet in the solar system, although Mercury is the nearest planet in the solar system. Incidentally, Mercury doesn't have a atmosphere. So now Kepler started searching for planet in the circumstellar habitable zone of various stars. Very soon, Kepler discovered a planet which is in the habitable zone of a star called Kepler 22, but it is found that the planet is much bigger than the Earth. It is of Neptune size, and therefore it cannot be rocky, it has to be gaseous. So even though it has the appropriate temperature for water to exist in liquid state, it cannot retain the water on its surface. To retain the water, so the planet needs a solid surface. So the search continued, and Kepler found another planetary system, Kepler 62, where a planet, this 62F is located. Two planets are located in its habitable zone, but still these planets are much larger than the Earth, and they may be mini Neptune or almost like Neptune. Finally, in 2017, a colony of rocky planet is discovered around a low luminosity, low brightness star, or that is called M dwarf star, which is called TRAPPIST-1 system. Now, out of 7 rocky planets, 3 of these planets are located into the habitable zone of these stars. But these stars are all very faint star, so their habitable zone is very near to their star, and therefore they are exposed to intense amount of ultraviolet ray and the stellar activity like flares from their star, and therefore even if they have appropriate temperature for water to exist in liquid, it is not known, it is not sure whether water really exists in them or water has been evaporated completely because of the ultraviolet radiation impinging continuously on this planet. So finally, in 2018, Kepler discovered a Earth-sized planet in the habitable zone of a Sun type of star, and thus this search continues, and we have discovered a quite a few candidate planets which are rocky and which are in their habitable zone. Now the question is that, can this planet really harbor life? Are these two conditions, that is the appropriate temperature and the rocky planet, are sufficient for the planet to harbor life? Can we really tell that they are habitable? Then we will land into a more fundamental question: what do we mean by life? Now, by life, we means whatever we see on Earth. Unfortunately, there is no other planet or no other place is found in outside the Earth where we can get another species of life. So the thing is that how we will describe life outside the solar system. Unfortunately, there is no fundamental definition of life. Now, say about 400 years ago, if somebody would have asked you what is water, you could have described only water. You could have told that, okay, water is a liquid, colorless, odorless, it travels from top to bottom. But if somebody comes with a beaker of methyl alcohol and tells you that, look, this is also a liquid, this is also colorless, odorless, so how you will distinguish it from water? So description, now what we have in life is a descriptive thing only. We can describe life. There is no fundamental definition of life. But today, if somebody asks you what is water, then you can tell that, oh, water is a molecule made of 2 atoms of hydrogen and 1 atom of oxygen. Now, from that fundamental formula or fundamental definition, you can derive all the properties of the water and distinguish it from methyl alcohol. Unfortunately, such type of fundamental definition of life is not there, because life is a system, is a biological system. But NASA has given a working definition for us, for the astronomer, about the life. So it says that life is a self-sustaining chemical system capable of Darwinian evolution. But it doesn't describe anything else. I mean, you can easily be confused by this definition. So now, if we consider the Earth type of life, that is the only life we see here, you can extend this definition slightly in a better way. So it says that life is an ensemble of organic material governed by a self-sustaining synchronized system of chemical processes and characterized by metabolism, replication, and evolution through the natural selection. Now, by what we mean by organic materials, that is the material, the molecules which are basically made by carbon and oxygen and hydrogen, etc. So life, Earth-based life is actually carbon-based. and it is governed by a synchronized system of chemical processes like enzyme, hormone, etc. And it is characterized by metabolism. That means the way it produces the energy. So when we breathe oxygen, this oxygen is carried by the blood and it get transferred into all the cells, and then this it oxidizes the carbohydrate and the fat in the cells and does generate energy. Once this blood circulation is stopped, once the heart is stopped, the oxygen supply is stopped, the energy is stopped, we can tell that the cell is dead. So metabolism also defines one more character, that is death. Replication is the function of the gene in the cell that copies, that makes exact copy of one cell into two, and it transfers the properties of one species into the next generation of species. The evolution through natural selection is the way a species respond to the surrounding. So we know very well that how a species, how the human being evolved into that. But the question now will arise. Some of you may tell that how do you know that the life outside the earth may be made of the same organic material, carbon based? Why not by silicon? Why not by iron? Why not by aluminium, etc., etc.? How do you know that life may be characterized by metabolism, replication? Well, so the thing is that the absence of evidence doesn't make the evidence. Now, if we put slight logic, then we can say that carbon is the most favored element to form life, because carbon is the fourth most abundant species element in the universe after hydrogen, helium, and oxygen. And also carbon combined with other atoms very easily and to form various number of the various molecules, and it is very easy to dissolve into the water, etc., etc. So so why the nature will choose some other element instead of carbon? Now we know that the laws of physics are same everywhere in the universe. That is Faraday's law, Newton's law, Einstein's law. Everything which are valid on the earth are valid in the far corner of the universe. But since we do not know any species outside the any living species outside the solar system, so we do not know whether the laws of biology are same or not. But the laws of biology comes from the chemistry, laws of chemistry, which are governed by the laws of physics. So if the laws of physics are same everywhere in the universe, why it should be different chemistry? Why should be different biochemistry? Now, even for the sake of argument, if somebody tells that maybe the life will be something else, but then we cannot recognize those form of life unless and until it is an intelligent life that tells us that, look, we are also life, and so laws of biology are different. Now, when we tell about the intelligent life, we come into another controversy. What do you mean by intelligent life? Now, we know that the human is the most intelligent species in this planet, or we consider that in our galaxy so far. But somebody may also tell that okay, monkeys are also intelligent, dolphins are also intelligent, even ants are also intelligent. But the thing is that for astrophysicists, the intelligent species will be said only to those species that has advanced in its technology, in its civilization, so that it can generate, it can receive, it can generate, and it can transmit artificial electromagnetic wave, that is, it can communicate to other intelligent life. Then only another intelligent life will realize that we have discovered another intelligent life. So in that sense, we have discovered the radio wave just 100 years, about 100 years ago. And in that 100 years, this level, this light, this artificial electromagnetic wave has traveled only 100 light years. So if the intelligent life, another intelligent life is located only within 100 light years, then only they can receive this signal. Now there is another problem is there, the origin of life. So far, about 50 years ago, Urey and Miller, two scientists, they synthesized organic material out of inorganic material in their laboratory. So from that, we started believing that then the organic material on the earth, that is the building block of life, are synthesized on earth out of the inorganic material. Therefore, we extrapolated that in that case, life is also originated on earth itself out of those organic material. But recently, we have got so much evidences from meteorite, from comets, that now there are more and more evidence that these organic materials are not only synthesized on the earth, they can be transported from outer space. There is a kind of object called asymptotic giant band star. At the end stage of this star, it is found that copious amount of organic materials are born around it, and they are carried by comets and other objects. And therefore, the question arises then if organic materials can be imported from outside, can life is also imported from outside? So can the seed of life came from outside, and it got a very favorable environment in our planet, and thus it survived and it evolved into the complex life and into the intelligent life, which can ask that what is the origin of life? Now let us see that. I have told that two conditions we consider that the habitable planet, but those are not at all sufficient. There are many other conditions that exist on Earth which are protecting the life. So let us see a few of these conditions. We know that the Earth has a terrestrial magnetic field. Now, the sun always emits copious amount of charged particle which travels towards the Earth. Occasionally, Earth get the sun get very much active, and it emits material, that is flare, which travels towards the Earth. Now, this charged particle or this energetic flare, if it could have penetrated the Earth atmosphere would have been destroyed, but the Earth magnetic field protected. This charged particle cannot enter through the magnetic field line. It can enter only through the open field line, that is in the magnetic pole, giving rise to the spectacular aurora borealis. So if this magnetic field was not there, then you would have seen this aurora type of thing in everywhere, and this charged particle would have changed the chemistry of the Earth atmosphere by reacting with the molecules in the atmosphere, and thus it could have made the Earth atmosphere completely uninhabitable. Now we know that volcanoes, we usually know that the volcanoes and earthquakes are very destructive. They kill things, they destroy the environment. But do you know that if there was no volcanoes and if there was no earthquake, then the atmosphere of the Earth could not have been habitable for such a long time? So now how? Now we know that carbon dioxide in the atmosphere of Earth plays a double role. It reflects, it acts as a albedo agent, that is, it acts as an agent to reflect sunlight, and thus it cools the Earth atmosphere. At the same time, it acts as a very effective greenhouse effect, and thus warm of the Earth atmosphere, or keep the temperature of the Earth atmosphere. Now, this carbon dioxide in the atmosphere mix up with the rainwater to form a weak acid called carbonic acid. Now, this carbonic acid, when it falls to the surface of the Earth, it mixes up with the rock and forms silicon carbonate. And in 1 million years, if this procedure continues, it could have finished all the carbon dioxide in the Earth atmosphere, and thus making the Earth much cooler. But because of the volcanoes and the earthquakes, this carbon dioxide again comes out to the Earth's to the Earth's surface, outside the Earth's surface, and into the atmosphere. And in 10 million years, it establishes a carbon-silicon cycle. And because of this cycle, the amount of carbon dioxide in the atmosphere is maintained properly. At the same time, volcanoes and earthquake also resynthesize the minerals on the Earth, and it resynthesizes the chemistry, the chemical elements or molecules in the atmosphere of the Earth. So in Mars atmosphere, this volcano or earthquake is not there, and because of that, the minerals in the surface of the Mars has not been synthesized for 4 billion years. Its atmosphere has not been desynthesized for several years. It remains the same. Therefore, volcanoes and earthquake plays a very important role in keeping the atmosphere of Earth habitable. Now, we know that the season here, the summer, the winter, and the rainy season, that occurs because the Earth's rotation axis is tilted in an angle. So this rotation, this tilt angle, presently at 23.4 degree, is also not fixed. This obliquity also changes with time. At the same time, the Earth's orbit around the Sun also changes from circular, near circular, to elliptical, to everything. So because of this dynamical effect, in every 25,000 years, we get a cycle that is called Milankovitch cycle, which is responsible for the ice or the snow age on the Earth. Now you see that this tilt, this position in the tilt angle is varying in 19,000 to 24,000 years. At the same time, it changes from 21.5 degree to 24.5 degree, currently at 23.5 degree in 41,000 years. And this ellipticity, the orbit around the Sun, takes much longer time, about 100,000 years. So this dynamical effect is very minor. The changes in the Earth atmosphere or Earth climate is therefore very stable. Now, what is the reason for that? Now, because of the presence of our moon, that is the presence of a large moon, this is possible. Now, the moon was not there during the birth of the planet Earth. So around 500 million years after the Earth was born, a giant object of the size of Mars, that is called Theia, that collided with the Earth. And during that collapse, the Earth was almost destroyed, but because of it is much heavier than this object, so it somehow survived. And the product that came out from the collision started orbiting the Earth, which is our present moon. Now, before the moon was born, the Earth was orbiting so fast that instead of 24 hours, the duration of one day was just 10 hours. So now this, if the Earth would have rotated so fast, and if moon was not there, then due to the gravitational force by Saturn, by Jupiter, the tilt angle of the Earth would have been much higher, and the change in the tilt angle would have been much chaotic. So this heavy moon, which is fifth heaviest in the solar system, but the ratio between the mass of the planet and the satellite, this is the maximum case for the Earth. So the moon plays a tag of wire between Jupiter and the Saturn, and it keeps the Earth's orbit so much stable. So for Mars, there is two small satellite, Deimos and Phobos, and therefore, although at present the tilt angle of Mars is almost same to that of Earth, but it moves very chaotically in almost some 100 million years. It changes chaotically to 70 degrees Celsius, and therefore the climate in Mars changes very chaotically. So if moon was not there, the climate would have been very severe on the Earth's surface. And therefore, in addition to giving rise the tide in the ocean, the circulation in the atmosphere, the moon has stabilized the orbit of the Earth. Now, we will not know all these properties of the planet from this side. So how we will find out this planet is habitable? Now, we will not go to find out the properties of that. Instead of that, we will search for biosignature on those planet. So how is that biosignature? What is that biosignature? Now, if you take a spectrum in the infrared of the three planets, that is Venus, Earth, and Mars, you can see plenty of liquid water in their spectrum, and carbon, but which is not there in Venus and Mars. Carbon dioxide is common to both of them. And then the biosignature, when you see in the Earth's atmosphere, you will get a signature of oxygen molecule and ozone in the atmosphere. Now, this oxygen molecule was not there at the birth of the Earth. All the oxygen atom was combined with other elements to form water, to form carbon dioxide, carbon monoxide, etc. About 3.9 billion years ago, a bacteria called cyanobacteria which started photosynthesis. And once it started photosynthesis and a certain amount of oxygen molecule came out from volcanoes and plate tectonics, the chemistry of the Earth atmosphere got entirely drastic change. It became oxygen rich. The species which were already born but was surviving without oxygen became poisonous to them and they could not survive. So only those species which could adjust with the oxygen molecule, they survived, and right now we have 20% in the atmospheric composition is oxygen. Now, when this oxygen goes to the upper atmosphere in the stratosphere, it get bombarded by the ultraviolet ray of the sun, and it get dissociated into oxygen atom. Now, one oxygen molecule and one oxygen atom combines to form the ozone in the upper atmosphere of the Earth. Now, this ozone, therefore, is originated from the oxygen molecule, which in turn is originated from bioactivity. This ozone is protecting us from the ultraviolet, the energetic ultraviolet ray. If this ozone layer was not there, then this ultraviolet ray would have penetrated to Earth's atmosphere. It could have come to us. It could have created mutation in our cell, and the evolved life at least would have been completely destroyed by that. So it is not only the environment of the Earth, the life itself is also making the environment so that life can survive in this atmosphere. Now, how this type of signature will get? So we'll take something called transmission spectra. So when the planet passes through the star, it blocks the star light, but then a part of the light passes through the atmosphere of the planet if the planet has an atmosphere. So this can be detected in a spectrograph. So when we take a spectrum when the planet is transiting, and we take the spectrum of the star when the planet is not transiting, and then when we subtract, we get the additional information of the planetary surface. So by considering this, we have also modeled very sophisticated numerical code to construct the transmission spectra, and right now we have some observed transmission spectra from giant planet Jupiter type of planet, and our model is the most sophisticated right now, and this can fit very well. We have also modeled the simulated observed data of JW SST, that is James Webb Space Telescope, which will take this type of transmission spectra, that is the spectra of the planet. But current technology is beyond the reach of taking the spectra of habitable planet, habitable rocky planet. But during this decade, or even slightly more, within 10 years, we are going to get some new generation, some next generation telescope. So I have told you that Hubble, you know that the Hubble Space Telescope is still functional, and it has taken the spectra of the giant planets, Jupiter-like planet, which are very near to the stars. Picture has taken quite a few spectra in infrared. Kepler has discovered almost 3,000 extrasolar planets. TESS is still functioning, and it is detecting new planet. This year, James Webb Space Telescope, which is 3 times more powerful than Hubble Space Telescope, is supposed to be launched, and then there will be a good amount of space telescope will come, out of which I am a collaborator of this aerial project that is by the European Space Agency, which will be a dedicated telescope for taking spectra of planet and to find out the molecules in the atmosphere of the planet. At the same time, we'll have some giant ground-based telescope like the European extra large telescope, like the 30-meter telescope with which we, the Indians, are collaborating, like the giant Magellanic Cloud, etc., etc. So we hope that within this decade, by using this next generation telescope, we will be able to detect the spectrum of habitable planet, habitable rocky planet, and therefore it may be possible that we may discover biosignature in some of the habitable planet, which can revolutionize our concept, or which can answer our question if life exists elsewhere or not. But before we discover life elsewhere, before we discover life beyond our own world, let us come back to our own planet. Let us see our own Earth, how it looks from the space. Our home, a pale blue dot. That's Earth, that's home, the third planet of an ordinary star called the Sun. An extremely rare combination of astronomical and geological coincidences enabled life to origin, survive, and evolve on it. From a distance of about 10 million kilometers, the Earth looks like a blue marble. As we move further and further, the planet appears as a pale blue dot floating in the vast emptiness of space. So special, yet so vulnerable. So crowded, yet so lonely. So common, yet so unique. So insignificant, yet so great. A mote of dust suspended in a beam of sunlight. So accept it or not, so far we have not got signal from anywhere outside the Earth that can tell us life, whether in intelligent form or even in primitive form, exists. But the space is a very dangerous place. So there are quite a few potential dangers to this rarest of the rare planet where a divine phenomena like life exists. So collision by a comet or a giant asteroid may destroy the Earth atmosphere irreversibly, but this possibility reduced because of the specific structure of the solar system, where the giant planet Jupiter, Saturn, Uranus lies outside in the outer region, and the inner planet lies inside in the interior region. So these planets, these comets and the giant asteroid that originated at the edge of the solar system known as Kuiper belt. So Kuiper belt is the origin of the small period or the medium period comets. But when it travels towards the sun, it could have bombarded the Earth atmosphere. But because of the gravitational pull by Jupiter and Saturn, the possibility, the rate of hitting has reduced drastically. But still, we don't know if one day one or two comet misses the blessing of Jupiter or Saturn, it may hit the Earth atmosphere. In fact, we believe now that 60 million years ago, such a comet collided with Earth. It destroyed the Earth atmosphere in such a way that when sunlight could not enter for several years, and all the evolved species, including the dinosaurs, got extinct in by this collision. Now, a supernova explosion within a 10 light year can produce, by a star, can produce such type of energetic gamma ray and ultraviolet ray that the chemistry of Earth atmosphere can change irreversibly, and the Earth atmosphere can become completely uninhabitable. Now, gamma ray burst, as Amit has already told about the gamma ray source. Gamma ray burst is the most energetic source in our universe. So even if one gamma ray burst takes place in our galaxy, the energy that it produces, it can destroy the Earth atmosphere irreversibly. Now, usually the sun is a ordinary star. It is a dwarf star. It's a very gentleman. It doesn't create any problem. Occasionally, there are some small flares or solar activity counts that disturb our telecommunication system. But if because of some unknown reason, some giant flare emerges out from sun, it can penetrate it can destroy the magnetic field of the Earth, and it can penetrate the Earth atmosphere, and it can destroy the Earth atmosphere irreversibly. At the same time, terrestrial hazards are also possible, like super earthquake, super volcano, super tsunami, etc., etc. But these all astronomical and terrestrial possibilities are very, very minor, very small. There is no indication that there is any nearby star will soon get into the supernova explosion, or if there will be a gamma ray burst in near a thing, or if there is no geological evidence that there could be a super earthquake very imminent, or a super tsunami or volcanoes are imminent. But the most imminent hazard is man-made disaster. So an accidental nuclear, chemical, or biological warfare can destroy the Earth atmosphere irreversibly. No, even after that, Earth may survive, but life may not survive, neither it can origin again. The global warming. As the civilization expands, we produces more and more carbon dioxide, and therefore the greenhouse effect is increasing, and it is warming the Earth atmosphere very alarmingly. So if the carbon dioxide level increases at certain speed, then it may also behave like the Venus atmosphere, and it may go as runaway greenhouse effect, and the Earth atmosphere will become tremendously hot and uninhabitable. At the same time, the ozone layer may be destroyed completely, and the ultraviolet ray from the sun would have entered into the Earth atmosphere and then towards us. At the same time, the carbon silicon cycle may also be destroyed if the amount of carbon dioxide keeps on increasing. Then there are scarcity of groundwater and all those things. So while searching for another habitable planet, while hunting for another habitable planet, while searching for life outside the our own world, while trying to get an answer of the eternal question, if anybody out there, we realize that our planet, our Earth, is so great, it's so rare, and it is our duty, it is our responsibility to first protect this planet so that generation of children can keep on smiling on it. Thank you. Now, if any of you are interested for further study of exoplanet and biosignature and astrobiology, you may collect my book written in popular level, A World Beyond Our Own. It was published in 2005 by Springer. Thank you.
Thank you very much, Professor Sen Gupta, for the lovely talk. If there are any questions, you can unmute yourself and ask, or you can send. Okay, all right. Priyankar Mukherjee has a question. I have heard that the moon is moving away from us. Can you
Yes.
say why?
Yes, the moon, because the moon and Earth is trying to be synchronized in their radiation thing. So earlier the moon was very near to the Earth, but then it is moving, I think, a few centimeter in every 1 million years. So now you know that the moon's rotation is synchronized with Earth, because it is it is tied up with the Earth gravitational field. So at the same time, it is trying the Earth also to become synchronized with its motion, and therefore the Earth is also slowing. The Earth's rotation is also slowing. So the moon is moving further, and the Earth's rotation rate is also slowing down, so that the tendency that at one time the rotation of Earth and the orbital motion of the moon will become the same. But that will take another 4 to 5 billion years. Before that, our sun will exhaust all these hydrogen and helium, and it will engulf the Earth, and so we will not face this problem right now. At present, yes, the Earth rotation period is reducing, and the moon is moving away from us, but in a very tiny rate.
Thank you, sir. Any more questions, please?
Yes, I have one.
Okay, sure.
So thanks for the nice talk. And my question is, how do we exactly search for exoplanetary system which are face on with respect to our line of sight, as both the methods you mentioned, that transit and
No,
radial?
there is no way except that if it can be directly imaged. Like some of the directly image planet that I have shown you, those are about 100 million years old because they are still forming. So they are very hot and they can be directly imaged. So those planets can be detected by direct photographing it by blocking their starlight. But still, they are far away from that. I mean, some of them are at the distance of Sun to Pluto. So they moves very slowly. So there is still we do not know whether they are face on or they are edge on, but we can detect in that way. In addition to that, there are other methods like gravitational microlensing. We can detect planets which are far away and which are very small. But gravitational microlensing, we cannot make out that whether it is what is this period or whether it is edge on or which is face on. So right now we can detect only those planets which are edge on or whose inclination angle is higher than 75 degrees.
Okay, thank you.
So the observation is biased in that way.
Okay, Priyankar has another question. He's asking, in your thermal map of the Earth, there were some gray spots. So what are those?
See, I'm not an art scientist. If you are asking me, I think better you ask it to the geologist that if there is a gray spot on the Earth. So that those spots are maybe the variation of the temperature. This is a complicated thing there. There are a lot of maps, or there are infrared maps, and there. So some region Earth's temperature is not homogeneous on the surface. Just like the sun, we see the sunspot. The darker region is actually the cooler region. So like that, if you take the infrared, and from some of the spaces, more infrared comes, some places less infrared comes. Optical radiation are better than that. So that makes the variation on it. So when you ask, since you are a student, when you ask that I have heard, you should tell that where you have heard and how did you come to know. And when you come to know or if you see something, then there itself you find out the references and about the details. Okay.
Thank you, sir. Any more questions for Professor Sengupta? Okay. Okay, there is a question from Chinmay Shahi. How do we verify if the brightness change was due to a planet or some other object in the path, like a comet?
Yeah, that's a good question. So we cannot tell that just by looking once. So usually the rule is that we follow minimum 3 times this transit, and then we see the period of this thing. If the period, so from the period for this type of planets, the period varies from few days to 1 year or half of a year. But for comet, and most of these planets are in the circular orbit, so that also we can find out from the light curve. But for the comets, they have a highly ecliptic orbit, and so only once you can measure, and then you have to wait for 70 years for it to comes out, and we can find out that the light curve will be quite different than the planet, because it is not only the comet head, because the tail will also block certain amount of light from the star. So far, one exocomet has been reported whose light curve was quite different than the light curve of the planet. Again, there are many other possibilities, like there is a sunspot, the star pot. So by monitoring repeatedly, we all rule out, and then modeling and removing all these systematic or permanent noises, we all confirm that this is not anything other, the source is not anything else, but it is a planet. And if there is a star, binary star, that also blocks, but then the binary star itself has some brightness, so there the variation will be different. It will be very narrow also, the light curve. So there are, we know very well that how I mean, so what type of noises and what type of possibilities are there and how to remove them, and then finally we confirm it. It's not so easy thing. I mean, from my talk, you may think that these are very easy thing. This is a descriptive thing, or from the transit method, just a photography. But behind that, there are lots of numerical, mathematical work. For radial velocity method, the instrument itself is a very complicated instrument. So to measuring a few meter per second radial velocity and that movement, you need to consider the movement, even the slight vibration of the observatory or the telescope, and the thermal variation as well. At the time of transit radiation, there will be atmospheric effect, there will be many other effects. So you have to reduce those noises by using very sophisticated computer packages, numerical packages. So all that we do, then only after that, those data we model and fit it and find out the parameters. These are for the follow-up. For the discovery thing, it is much more complicated, because all those other effects, you have to include the other possibilities, like a unresolved presence of unresolved star-like object, or a brown dwarf, or a comet, as you have told, or the sunspot, or some activities of the star. Those are the things. So this analysis that is very complicated, and this is very time consuming. We use cluster computer and to reduce the transit data that we obtain from two of our telescope, and from then only we can model the data and tell the physical properties of the planet.
Okay, there is another question from Hemant Kumar Sahu. Why the sunspot, that is pair of spots, appears only approximately 12 years? Yeah.
I think people have given in this winter school talks on sun, right? It is discussed already. So I do not want to talk on a subject which I am not expert, or I don't. So I think it's better this type of question, like the Earth image or the sunspot. This should be asked to the appropriate expert who has already, I think, given solar physics. Who has given Avirup in solar physics? I think Dipankar has given a talk on solar sun.
Yes, yes.
Yes. So
The
I should not confuse
particular
you or tell it I am not a solar physicist. Okay.
All right. More questions are always encouraged. Please go ahead. I know there are a number of students here. So
Yeah, you can unhesitatingly ask, but please keep your question within the topic, that is planet or extrasolar planet. Just consider that I don't know any other subject. I am stupid on that. So if you ask me what is dark matter, dark energy, sorry, I should not answer those type of questions, since there are many experts who are present in this winter school. Anybody?
yeah, we easily have time. So, and this is an exciting topic, not one that we hear every day.
So nobody asked me about exomoon. Nobody asked about diamond planet. You have not heard all those things, is it? I'm asking the audience.
Actually, sir, may I ask you a question, if that's okay?
Yes, sure. Yeah.
So, have we been able to detect any exomoons at all?
Yes. So I gave you the hints and you are asking the question. Yeah, it's very difficult thing. It is very difficult thing because it is very small and it is a many body problem there. So we are planning it means yeah, effort are being made. In fact, I have proposed a new method that is polarimetric method through which exomoon can be detected. So the groups in Caltech.
I'm sorry, sir, your voice is cut off. Yeah, okay.
Yeah, but so far exomoon has not been discovered, but there are methods which are called TDP, means the time variation in the transit light curve or through polarization or through such type of thing. But these are extremely difficult to discover planets, I mean satellite, the artificial satellite, the natural satellite around a planet, which uh, which are of Earth size that is nearby. So if there is a Ganymede size of planet, it will be easier. But the means confirming it or to find it out, the variation it will give to the star will be so negligible that it's extremely difficult. But we expect that the next generation telescope may give some hints or may give some indication of the presence of exomoon around some of the planets.
Hello, can you hear me, sir?
Yeah, sure.
Yeah. I was just wondering, in light of what you have said about the Earth's moon, what if we were somehow able to discover a moon equally large, and let's say we discover a system which has something like an Earth mass planet, and whose moon is roughly the same size and mass. What is there any inference we can draw from this?
Well, you are just speculating. So a moon of a size of Earth cannot be as big as the size of Mars. Our moon is much smaller or much lighter than the Mars, because in that case it will be just like Pluto Charon type of system. The very center will be, see, for moon Earth system, the very center, the center of rotation is inside the Earth. Even all the planets very center are inside the sun. But for Pluto and Charon, the very center, the center of motion is outside the Pluto. So it is like just a binary planet type of thing, and that is one of the reason why Pluto is considered no more a planet; it's a dwarf planet. So it's not possible to have a satellite, natural satellite of the ratio 1:2. See, the Mars is nearly half of the Earth mass, or I think 1/3 of the Earth mass, and the size is also almost half of that thing. So such a big object will not orbit around the Earth. Either the configuration will be destroyed or this will be a binary type of planet. But I don't know if that is possible or not. In fact, actually, the satellite, there are many satellites in solar system. Like the largest one is Ganymede in Jupiter. There are Europa. There are many things there, but not all the satellites are formed in the same way moon was formed. The large satellite around Saturn or around Jupiter were formed just like the planet are formed. So it's a scaled down planet formation type of thing, the way. So once the planet was formed, the remaining amount of dust and gas that made those satellites. On the other hand, the collision theory of the formation of moon is much accepted right now. And then Triton, it might have come from Kuiper belt and got attached with Neptune, the Uranus. So like that, the origin of the satellite in the solar system are different, but their mass ratio is much less compared to the planet. Even in fact, it's a very surprising thing that such a massive satellite Earth has, which no other planet in the solar system has. And incidentally, this is, whether it is a coincidence or not, such type of satellite is protecting our life, as I have mentioned it. So I do not know if there were 10 satellite, 10 moons would have been a blessing for the life on Earth, or it will be dangerous for the Earth. But even one planet is quite sufficient for helping the life to survive and to evolve. So that's a wonderful thing. Yeah.
Thank you, sir. Thank you very much. Okay. I had a silly question, if you don't mind.
No.
Is it?
Question? Nothing is silly.
I was just wondering how practical it might be to, because I know next to nothing about chemistry, how practical it would be to have silicon-based life.
You see, I told silicon-based life because silicon is the same in the same column of the carbon, right? It has almost all properties of the carbon. But the thing is that you know that silicon needs more energy to combine with other element to form, and so silicon cannot make so many varieties of molecules and long chain of molecules like carbon make it. And also its binding energy is like that it can easily be destroyed in that way. Therefore, silicon life and silicon is not that abundant than carbon. Carbon is available everywhere. In fact, the solar system, in the solar system, carbon is half of the abundance of oxygen. But silicon is not in that abundant system. So chemically, it will not be favorable for because you need varieties of large varieties of millions of molecules that can be formed with a long chain by that element. So that is not possible by silicon. That is possible by carbon only. But anyway, if you think of a higher type of thing, such God type of thing, it may be made of silicon, which may be transparent also in that case. You cannot see it. So nice to imagine, but logically, thing is carbon is the best, I think, element available in the universe for using of making life. If you were God, then how you would have made this life? Had you taken the most difficult way, or you would have taken the most simple way and first form the one cell amoeba and then let it evolve automatically and then make into the evolved life? No, you will not take the difficult way. You will take the most easiest way, and then you will make the thing. So imagine in that way. So carbon is the I think the most favorable element, not the silicon. Any more?
Thank you, sir. Thank you very much.
Thanks a lot. Thanks a lot for joining.
Thank you. Thank you very much. And thank you again for inviting in this winter season. I'll be attending Ajit's talk also. So I'm not exiting it. Okay, so you can start I think already it is 5 o'clock. Okay.
Yeah, we're actually waiting for Ajit to join. So he has some technical issues at his end. Wide network outage.
Okay, so in that case, you can continue asking me question. If anybody has question, any student has question, nothing called silly question or crazy question, you can ask any question.
So there is actually one in the
regarding planet
chat.
Or anything you can discuss.
Okay, I think there is a question from Hemant. Does Neptune-sized planet called ninth planet really exist?
That's a good question. So the thing is that see how Neptune and how Uranus, how Neptune and how Pluto was discovered. So when Uranus was discovered, it was found that its orbit is deviating something. It's not exactly following the Kepler's law or the other laws known. There is a time delay. So it was predicted at that time that there must be another planet outside there. So in that way, Neptune was discovered. Now, when Neptune was discovered, then also it was found out some perturbation in its orbit. So there was another planet, ninth planet was predicted, and that was Pluto. But after we know that the Pluto is a very light, it is lighter than even Moon. So we know that this perturbation cannot be explained by Pluto. So then Kuiper belt was discovered. There are many things are there. Now there are some Kuiper belt objects, these dwarf planet like Haumea and like Eris, all those planets which are Pluto. So it is found that they are moving in a particular direction. So their orbit is somewhat peculiar, which can be explained only if there is a gravitational, some gravitating body. So that's give the doubt on the presence of a ninth planet. So NASA sent a satellite called, I think, WISE. So WISE surveyed that region, and but WISE could not find it out in infrared region, but it gave a upper limit that the planet, if it exists, it cannot be bigger than Saturn or even Neptune. So now it is believed that there could be a ninth planet, either it's a super Earth or a Neptune-sized planet. But since it is a far, far away from the sun, and so it is completely very, very dim, and its orbit is also very, very large. See, even Pluto cannot be detected so easily. So it is very difficult to detect this ninth planet, but I hope that JWST will give more information. But if discovered, this will be the last station of the solar system. Because the solar system formation has a limitation, so there cannot be any more larger planet beyond this ninth planet. So a possibility of a ninth planet remains. In that case, if it is discovered, we will get back to again Naya Navagraha, and that will be the end of the story of the solar system planetary objects.
Thank you, sir. Okay.
Yeah, thanks a lot. I mean, I don't see Ajit coming in, so
Okay.
let us wait for a little bit of
Let
time.
me
I think
tell
he's trying to join.
something that how we do the observation. We have got recently this 1.5 meter Jagadish Chandra Bhattacharya telescope, and by using that, two of my students, one is was an engineer, Jadavpur University, electrical engineer, but he was motivated in astronomy, so he joined the IIA's integrated MTech PhD program, and he started doing the observation. Then we together developed this numerical code. So if any of you are doing engineering courses, you can also think of considering coming to astronomy and can take part in that. It's not just like putting an eye on the telescope and see, that is amateur astronomy. You want to become professional astronomer, then it's a very exciting field, and we need help from engineer, physicist, and even sometimes the computer engineers also. Similarly, in Himalayan Chandra telescope, also we do it. Sometimes what happens, the telescope gets problem, so we ourselves has to repair it immediately like that. And then the thing is that the modeling part is also needs very high expertise on numerical code. Usually, when I was a PhD student at that time, Fortran and Pascal was available. So all my codes are now converted into Python code. So therefore, we need young people who are very efficient in computational aspect, and also who are more motivated and keen. Who knows that one day one of you may discover the biosignature, or you may discover a exomoon in future by using Indian facility, the Indian existing facilities.
Thank you, sir.
Amit, are you there? Amit Sugla? I can see him, but maybe he has switched off. Is it? Yes. Mute down. Amit did PhD from our institute, Indian Institute of Astrophysics. So my previous speaker, Amit Shukla. It's nice to see him after a long time.
Yeah. Yeah. Thank you very much, sir.
Ajit has come already.
Yeah.
Thank you, sir.
Thank you. Thanks a lot.
Yeah. So I'll be there, Ajit, in your talk.
Sure. Yeah. So Siddharth, you can take it over. Yeah.
Yeah, sure. It is a pleasure and an honor to welcome Professor Ajit Kembhavi. Very briefly, not that Ajit needs any introduction to all of us, but very briefly, Ajit did his BSc and MSc in physics from Bombay University and his PhD in physics from TIFR. And his research interests generally are extragalactic astronomy, high energy astrophysics, particularly X-ray and radio pulsars, and more recently gravitational astronomy, particularly the Indian LIGO instrument. So without further ado, Professor Kembhavi. Sir, can you hear us?
He has muted it. Ajit, please unmute your microphone.
Hello, Professor Kembhavi. Can you hear us?
Can you hear me now?
Yes, sir. Yes, sir. Of course.
Can you hear me?
Yes, sir.
Can you
Yes, sir. We can see your screen. Yeah.
All right. So I'll see how far I can go because, as I said, it's very unstable. But my guess is that once in a way, once in a way is today. So I'm going to be talking very briefly about the Indian space program and the science. So the topic that I have given actually is astronomy from space, but I shall come to that halfway through my talk, because I thought that it's also good to know about the technology of the program itself, which is very central to our being able to do the astronomy from Indian facility. And needless to say, the technology by itself is very important. Sorry about that. Now, I'll first tell you about the launch vehicles and the satellites that ISRO typically uses for its purposes here for going into space. And we all keep hearing about the PSLV, which is a polar satellite launch vehicle. And this has been the workhorse of Indian astronomy, the Indian space program. It has had remarkable success, meaning that in several dozen launches, there have been just a couple of them that have been unsuccessful and none at that. So this is a 4-stage rocket with alternative solid and liquid propulsion stages. So I shall not be able to go today to why you use the liquid and solid propellants. The question of efficiency and ease of using them and so forth. So this is a massive structure, 44 meters, 320 tons, and it can carry a payload of between 1.8 and 3.4 tons, depending on the orbit. So which tells you which means 1% of the mass of the rocket can be in orbit. So clearly, you need to improve on that, but that is technologically extremely difficult. So then we have got GSLV, which is Geostationary Launch Vehicle. This is a 3-stage rocket, again with solid liquid, also a cryogenic stage. LOX, I won't tell you what's LOX and LH2 as fuel, and it's at extremely low temperature. It's very high efficiency. and has been.
Professor
now
Kimberly, I'm sorry.
launch. You'll see here that about 640 tons, and the payloads which we can use go from 4 tons to 8 tons. So which means that as far as space observatories are used, send out much more sophisticated observations. Now the kind of the orbits that you can put into satellites, one is you call the polar orbits, actually crossing the poles. Then if the satellite is equatorial, you can get the geostationary orbit. The ones which we are most used to, where the rotation period of the satellite is exactly equal to the rotation period of the Earth. As a result, the satellite appears to be just 1 point. I see our TV programs, for example, the satellite is always in a, if it, then our crew would be able to track what are the satellites, different kinds of satellites that we have, which means what are the different applications of the satellite. The most useful, of course, are the communication. To hear talk today because of the way of such communication satellites. And for Earth observation, things like Cartosat, Sat is we are carrying out a project for mapping the tree cover of Pluto. And for that, we are going to depend upon maps from, and it will be possible. The resolution is so high that we'll be able to good estimate of the properties of individual trees. Then you've got satellites for navigation. Satellites, Astrosat and Aditya, which I'll explain. And then there are things called academic satellites, Kalamsat, Swayam. So these are small satellites, maybe even CubeSats, which are built by academic institutions, including colleges, and then they are put into orbit, and they carry out some specific function. The rockets, we have got the satellites, instruments, and so what are the kind of missions that we carry out? Programs go. The main missions are the lunar and planetary missions. You to move and go to the planet. So you know that people is going to and to Mars. We would like to move further away towards Venus, and all these missions are in. So you having any one of these missions technology. So this is completely done within India. Sometimes you need to depend on the source of software and so forth. We also need the tracking stations, but open India therefore. So these are technology demonstrators. So if you can go to Mars, it will you'll see how accurate the orbits have to be. Send this craft out to such great distances, face formidable difficulties, and then to get them to perform a function for you. So the same technology can, of course, be used for other purposes. So the technology. So you're going to set up missions. It's an old mission, 2008. It carried scientific instruments and 11 scientific instruments. It's a very successful mission. So here you have got the spacecraft itself, and like all spacecraft, panels and antennae and so forth, and then instruments which are placed around it. Though size is not terribly large, because as we have seen, the amount of weight which can be carried is limited. The 8 tons, and the power it gets from the solar panels is 700 watts. So what you have to do here is that you have to be extremely careful with everything that you put. So it cannot be like an Earth, like a telescope, where a little bit more and less will do. You have to be very precise. As you may know, it takes a pretty long time to design a satellite. To design a satellite, to put it, test it, and then to for space, and then finally get it ready for launch. It can span a few to several years. So even the complex missions like AstroSat, it longer. And the point is that during this long period, technology changes. So you know that over a 10-year period, computer technology changes very dramatically. The bandwidth technology changes dramatically. So we should mean that from the time that a satellite is designed to the time that it is actually launched, there's so much progress in the technology that you feel, why are we not using the new technology? It would make the satellite so much efficient, so much more productive. The point is that, as I told you, the the design is excruciatingly difficult, and all decisions have been taken in advance. And once it's frozen, it cannot be changed. And you'll have to throw away the satellite and make a completely new one. And therefore, you learn to work with what you have in the original design. See, orbit, what is involved in going to the moon. So you launch from the Earth, then you send satellite to the orbit. So it will be typically an elliptical orbit. So you know that from orbit, from Newton's things, how the orbits are. So if I give a satellite a certain amount of energy, the moment it will go in an orbit, which and the Earth will be a focused orbit. If I keep the same momentum and extract energy from the orbit, then have the eccentricity will be reducing, and the orbit becomes a circle. So we don't want that. What we want is that we want to shoot the satellite to the moon. So here you start angular momentum and certain energy, and then you keep giving it more and more energy. You keep firing the more rockets. You see, the PSLV and the GSLV carry the satellite into orbit, and then all the rockets just drop off, and there is just the satellite. But the satellite has small engines in it, and these engines can be big maneuvers. So here you have engines, therefore you accelerate the satellite, and then therefore you are giving energy to it. So you'll see that gradually the orbit becomes more and more elliptical, and then it has reached sufficiently close to the moon. So I have to extremely tricky maneuver, and it involves now slowing down the satellite. So first you are giving it more and more energy because the orbit becomes elliptical and moon. But here what you require now is to slow down the satellite, because you see that the gravitational field of the moon is very much slower than the gravitational field of the Earth. Too fast, it will simply go away into space. If you slow it down too much, then it will fall into the moon. So therefore, what we require is just a precise amount of deceleration which extracts energy from it. So for the given angular momentum goes into angular momentum.
Hello,
Now
Ajit.
the satellite once in a way, so that gradually you are extracting energy from the satellite, and therefore it now becomes, it goes in orbit around the moon, and the orbits have become circular. Now around the Earth, you cannot have an orbit very small radius. The satellite moves to the atmosphere, it will get quickly burnt out. But around the moon, you have got the luxury of no atmosphere. Okay, so therefore the satellite can in principle approach the moon really close. So you see that satellite into the orbit, it obtained data. Now these are three-color composite reflected near infrared radiation from the sun. So you've got the radiation forming, and then you look at the near infrared reflected part. So you've got near infrared detectors. And what is the purpose? The mineralogy mapper. We want to see the minerals available. You use three colors, and then calibrated, you add them together and you're calibrated the colors that you see. So you know that iron, these red ones here are iron-bearing mineral pyroxene with 1 micron. Here you got water at 3 microns and reflected light at 2.4 microns. So you see that you are actually spotting water on the moon. And then you see here, and this is all very well known now, the water on the moon is subsoil water. But here you're actually seeing water in the craters. And you see that this is the northern hemisphere and this is the south. And there are the deep craters here. And the water is mostly in the craters. And what happens is, you see that the Earth's axis make an orbit. And therefore, the North Pole and South Pole face the sun. Here, the inclination is very small for the moon. As a result of which, many of the craters on the South Pole never see sunlight. And the temperature remains rises about minus 156. So, so you got the water remains there. Ice. Then the another thing was is that a probe just impacted the moon, and the dust from the moon was also looked at. And then you can see this moonshot, the beautiful picture. You can see the remarkable resolution that our cameras achieve. They are very well known for these high resolution cameras. And finally, the mission ended. The communication with it, I was expected that it will go on for 2 years, but communication with it broke off in 12 days. So then after that, using Earthbound radar, NASA was able to spot the much later. So spacecraft was 2016 by NASA. So then the next I want to consider very quickly is the Mars orbiter mission. So see, same kind of thing. The objective is the same: development technology, and then a certain number of science objectives which are carried out by many institutes and departments of ISRO. And the orbit is the same. So you start with elliptical orbits, and it goes towards Mars, and then it gets trapped by Mars. So, so you see the problem here. The distance is much longer, so you have to plan for the movements of the Earth and Mars in a much longer period. So you can see here that the launch was on 5th November 2013, and then the Earth was at this point here, and Mars was here in the orbit. And then by the time the satellite actually reached Mars, so it was, I mean, this hidden, my view is hidden by this panel here. It was September 2014, and that is where Earth was, and this is where Mars was. Mars that we have got here, and the close-up of the Tyrannus Mons, the mountain, and these are all the science results which were obtained from it. Chandrayaan 2, very briefly, and we know that it was launched on July 22, 2019. It reached and then the lunar orbit on August 20. And we saw this live on TV, you may remember. And then the unsuccessful soft landing on the moon. Contact was lost 2.1 kilometers from the lunar surface. So this is always a great risk in all these space missions. You work for a decade, you send out an important satellite, and then just at the last moment, something can happen. So this is the kind of risk that you have got to take. But our missions, on the whole, have been highly successful. Two are the one. There's a moon with Japan, which will involve actually a rover, a lander, and a rover. There's a Venus mission, and then there's a Gaganyaan mission with astronauts. So that it's a completely different ballgame when you actually want to send human beings into space, because you send them into space and you got to bring them back, and you got to bring them back alive. So that introduces completely different risk factors and so forth. But they decided to go ahead with that. The people who are selected, so they need to be highly trained pilots. So they're typically test pilots. So you must have heard about the first person to go into space, and that was Gagarin. And when that happened, I was very, very young. I was just a little boy. But it became very famous even in India. And a great test pilot. And then he finally died in a crash during a test. Space astronomy. So you know that we have got astronomy from the ground. We have got telescopes, we have got large telescopes in the deserts, telescopes on the mountains, telescopes in the middle of the sea, Antarctica. And these are all in different places because the atmosphere, there are different properties. We want to emphasize certain kind of observations. So now the question is, why do we want to go into space? Now, if you take something like the Hubble Space Telescope, and I have heard that the amount of money which is required to keep it in orbit for a year is much more than the amount required to build a great telescope on space. Right, and Hubble has been going on for a very long time now, well more than 25 years. So the question, why do you do that? When it is so expensive to just keep it in orbit, you can imagine how expensive it is to send it there. So why do this? There are two reasons. Okay, so why space? One is the opacity. It is basically, both the reasons depend very much upon atmosphere in two completely different ways. So one is the atmospheric opacity. The atmosphere has got gases, and ones which bother us are, you heard about O3, and then there's water vapor, which primarily absorbs infrared radiation, and you've got carbon dioxide. So you see that this is a very broadband picture of for the opacity, which means that how opaque is the atmosphere. So if it is 0% opacity, it means all the light at that particular wavelength coming in through the atmosphere. Whereas if it is 100% opacity, it would mean that no radiation whatsoever. Light here, I should say radiation. No radiation whatsoever comes in. So this is a 0.1 nanometer. So this is the if you look at frequencies, we're talking of 10 to the 15th hertz. So you see that here you have got it's basically gamma rays, X-rays, and ultraviolet radiation. And here the opacity in the atmosphere is 100%, which means that you simply observe it. So now you see, we always wondered, we meaning astronomers always wondered whether the celestial bodies would be emitting X-rays. For example, we know it's extremely hot in the inside. Outside temperature of 6,000 Kelvin. If it's so hot, and also the atmosphere, and it should be emitting X-rays. But we had no idea whether it was X-rays. And finally, it does. Completely outside the atmosphere. The rockets, they just go up a little bit. They manage to catch the X-rays from the sun, because it is extremely luminous in X-rays, but it is very close by. Then you can actually put your X-rays, X-ray instruments on balloons and send them up. And the IFR, for example, for years carried out a program like that, and they have been that is looking at X-rays from the balloons. But if you want to do that for best effect, and then you need to put the instrument on a satellite and send the satellite in an orbit outside the Earth. So here, this is for X-rays. But here, you see that when you come to the optical opacity, and which is the sun and the stars and everything else in space, if the opacity were higher, we would have been completely blind to the existence of the universe outside Earth's atmosphere. So, but then as you go towards the cross the near infrared, about 1 micron, 10,000 angstrom, and go into the infrared and far infrared. Again, the opacity has many spikes. Then it is completely opaque in this region, and then again. So you see that you on optical you have got enough telescope on the Earth, but then please understand that the Hubble Space Telescope actually works at optical wavelengths and infrared wavelengths. So if it works for optical wavelengths, why do you have to go outside that? Why not make a much bigger, much cheaper telescope on Earth? Because on the Earth we now have many telescopes which are 10 meters and so, not many but several, and but the Hubble Space meters in diameter. So the question is, why do you need that? So the reason is simple. It's again the atmosphere which creates problems for the images of Hubble. So this is the red giant star Betelgeuse. There are a few stars which can be resolved, and if you actually look at it with a time resolved detector, this is what you will see. You don't see the steady light there. And in fact, when you look at the star with our eyes, you see that the star is twinkling. So why is the star twinkling? So that is because there is atmosphere. There's a lot of turbulence in the atmosphere on different scales. And because of the turbulence, the refractive index along the line of sight from a star to our eye keeps changing. So look at consider a beam of light, a ray of light which is coming from the star to us. It has to enter our pupil. But because of the change in the refractive index, and sometimes you see the star and sometimes you don't. And the net result is a twinkling stellar image that you see. And here is that when you got time resolution, then on the detector you can actually see these things, these dots which are jumping around. And this is called atmospheric seeing. And the net result is that the image is expanded out in a Gaussian. It's not actually fully a Gaussian. There are other forms to the shape, but you can be good for the understanding. So this, if you plot the intensity in 2 dimensions, then you have got a shape like this, typically start with a star. Whereas if there are no atmosphere, then you should just see a line here. The line is slightly broadened because of the diffraction effects of the telescope. But otherwise, you get just a point source. So what does the boy do? So you see that this is the image that you get for a point source. And supposing I got an extended object, and because of the atmospheric seeing, you get a process which is known as image convolution, that the image gets broadened out. So what looks like an elliptical thing here is not the real underlying shape. The real underlying shape is circular. Objects can also, the broad objects can mix to each other. So if you've got 2 stars which are very close to each other, here the Rayleigh criterion, when you apply it, if the stars are like this, you get that they are resolved. 1.22 lambda by d is the distance which is required. When as the stars move closer together, here you see that they are barely resolved as individuals, and here they are not at all resolved as individuals. So you lose the resolution. You affect the image size and you lose the resolution. Therefore, what you decide to do is to build an observatory. It's called the Hubble Space Telescope, and you send it up into the atmosphere and you observe objects. The result of going there is a point source observed from the Earth will typically found to be spread out in a disk which has got which has got a full width at half maximum of 1.2 arc seconds or so. But here, when you go up, become diffraction limit, which means that the point spread function is less than 0.1 arc second. So you see what happens here is that there's a globular cluster called M4, and you see that this is nice, very good ground-based image that you see, okay? And then you see from here that space telescope out. And you see circles here. Each circle is enclosed in a white block. The power of increased resolution. increased resolution allows you also to look at very, very faint objects, to resolve objects first, also to spot very faint objects. And improvement to the science that you get is therefore considered uh, uh, is considered to be well worth the effort and the cost of putting a telescope in orbit and keeping it there. So what I'm going to do now, in time remaining to me, is to consider an extremely successful X-ray multi-wavelength X-ray mission, a multi-wavelength mission called AstroSat, and then I'll describe to you a mission which is going to be launched soon, in maybe a year and a half or so, and then talk about a couple of future missions. So Astro is a multi-wavelength mission, meaning that you can see here in this electric diagram that there are 5 different instruments. This is LAX-PC, this is a soft telescope. Here you have got the cadmium CZ detector imaging, and then here you have a thing called the soft X-ray SS, and then a very successful ultraviolet imaging telescope. 5 detectors here, and then the important thing is that they all in the same direction except the SSM, which scans the sky. So what happens is you're observing the same object with different wavelengths. But many of these objects which emit X-rays are highly energetic, and therefore they vary very rapidly. So if I first observe them at this wavelength and then at the ultraviolet wavelength, sometime later, the properties could have changed. So it makes a very big impact to actually observe them simultaneously. And you do that by putting all these telescopes pointing in the same direction. So this was launched on September 20th. Life for 5 years. We are already into 2021, and it's going pretty strong. There are one or two telescope components which are now gone dead, but still it continues to observe, and it's expected to go there for a few more years at least. It's a remarkably successful mission. So you see here the orbit of the satellite. It's a nearly equatorial orbit, and so you see the orbit is the equatorial orbit with a small inclination of 6 degrees. The orbit is carefully chosen because the satellite can pass through regions of the atmosphere which could lead to bad observations, absorption. Avoid that, to avoid that. So the orbit is very carefully designed. Okay, so the orbit is nearly circular. The distance with the satellite and the surface of the Earth, that is the longest distance. The semi-imagined axis of the orbit from the Earth's equator is about 7,000 kilometers, and the satellite goes around with a period of 97.6 minutes. So it has got, as I told you, it has got 5 detectors. And you see the UVIT is operating at the ultraviolet band. The soft X-rays, these are low energy X-rays. The LAX-PCs going to pretty high energy X-rays, and the CZTI, the mix of the bands. Go through, and here you see the LAX. So this is the set of. So there are. I'm showing one unit here. There are actually 3 identical units, one of which is not operating at the present time, I believe. These are 3 identical what are called. So meaning that as an X-ray passes through, it creates an output, ionizes the gas and therefore the pulse, and then the strength of the pulse is proportional to the energy which has been the energy in the X-rays. Now, the way the detector is built, it is used to maximize the area of the detector, maximum of X-rays, and ensure a high X-rays. Why do you need higher flux? Because you can then you can think quickly, and you can take observations even in milliseconds, and then the object under observation varies at different time scales. But the cost to that, the flip side, is that your resolution in the sky is poor, so you can't get an image of the object. And also the energy resolution is only moderate. So here is another, the soft X-ray telescope, built in TIFR. And though I cannot, what you have here is you see the remarkable thing about X-ray telescopes. So this is actually X-ray detector. Now consider an optical telescope. In the old days, there used to be refracting telescopes. So now what is that? It is use mirrors. So typically, you've got a mirror which is a paraboloid or some other shape like that, and there's a primary mirror, and then it has got a large area, and you point it to object in the sky. So you see that the greater of light which is connected. So if you look at then we have got a lens with a diameter of 8, and that is the collecting area. But if you look at the Keck telescope, for example, so it has got a diameter of 10 meters, right? So you have to take 10 meters and then divide it by, say, 1 millimeter, just for example, which is 10 to the minus 3 meters, and so you get a collecting area which is collecting a diameter which is, and therefore area is 10. So you see that is the amount of light, extra more light than the Keck telescope will collect to the eye. But look at the exact mechanism of the thing. Light from the star will fall on the paraboloid, and it all comes to, if the star is a point object, so all the light from the star comes to focus at one point, and that is where you keep. Now, if you X object that a galaxy, then instead of getting at the focus, an image of the object in the focus plane. But what is the mechanism? The light is falling onto the mirror and is being reflected. The problem is that you need a mirror for X-ray, meaning you want to reflect the light of X-rays which are coming from the object. That will not, because if you take the X-rays will actually not be reflected, they'll pass in the mirror, they get out. And therefore, what do? Glancing incidents, meaning that you see here in the telescope, you see these circles here. So each one of them is a cylinder, and the X-rays will be incident from this side, pass through the cylinder. They don't pass; they actually reflected in the same way from the cylinder, and then they come to a focus. Rather complex to understand, but this is what produces an X-ray telescope. Okay, then you have X-ray detector. Telescope. So you've got actually two telescopes here, side by side. It has got a collecting area of, I believe, 300. Yeah, it is the primary mirror is 37.5 centimeters in diameter. So that is small compared to the large telescopes we have here. But the fact is that the large telescopes can't detect the UV at all, and we have been remarkably successful in making interesting observations. This is a particular C2336 taken on the ground. This is an image on the ultraviolet space observatory called GALEX, and you see now it's nice. But now you look at the image taken by the near ultraviolet and the ultraviolet UVIT on AstroSat, and you look at how wonderfully resolved it is compared to the GALEX image, and that is what gives AstroSat a very large edge on. So here you see something called a Whale nebula, and this is the UVIT of the Whale nebula. Here the picture, and the UVIT observations refer to just a little bit here. Recently, several months ago, very remarkable result was by Kanak Saha and others from Ayuka, and they had a collaborators from abroad. So what they did, they put together many frames of imaging data from AstroSat. They added the frames together, the same frame, the frame of the same part of the sky, add them together. The adding is very complex because each picture will be taken from a slightly different angle, and so you have to shift and rotate and do all kinds of transformations to make all the images have the same form. And get the AstroSat ultraviolet deep field. And you can see here images that you get here, and it is for extremely difficult data analysis. And then they made a remarkable discovery. There's something called you see the question is that in the early phases of the universe was in the early phases the universe the material of the universe was ionized. The question is what kind of photons are they believed to be more energetic photons from galaxies, but such galaxies were very difficult to find. And in this research is done using the paper in Nature, which said that AstroSat detection of diamond alpha continuum emission of the galaxy at equal to 1.4, very difficult. And you see that here's a report on the paper: escaping photons finally arrested, finally detected. Actually, this is very complex. I cannot describe to you that easily, and we'll have to leave that for another time. So here is a gamma ray burst, which is detected by the CZTI detector. Time to actually to design it, to build the instruments and set it up. It was late, but having gone up, it is performing a wonderful job. So now very quickly, the next mission, Aditya L1. L1 is the first Lagrangian point. So here we have got an image of the sun. If you look at it, you get different images here. This is a corona that you see during and here the magnetic field lines of the sun. Of the sun. What we take is the atmosphere and the atmosphere, and then you have got the corona. And then you want to observe the different phenomena. You want to observe all these photosphere and the chromosphere and the corona at a very high resolution. You want to carry out different measurements which lead you to different properties of the sun. So here is a mission which is known as Aditya L1. Why L1? This is the first Lagrangian point. So you see that I show it here in this diagram. So you've got the sun and you've got the earth here. This diagram is of course very exact. And you see, you can imagine that when you are very close to the earth, if the gravitational field of the earth, which is dominant. But then as you move away from the earth, you eventually, the sun becomes dominant. And at a particular point, and this is not shown to scale, it is much closer to the earth. It's only 1.5 billion kilometers from the earth. The total distance is 150 billion kilometers. So at this point, at the first Lagrangian point, it is like the gravitational field of the earth and the gravitational field of the sun, and then the centrifugal force due to the rotation, they cancel. And that's a very important point, because if you keep a particle here, it will remain at that point. I'm of course being very simplistic, but that is what rough happens. So the idea is that you launch a satellite from here and you keep it here until the satellite keeps pointing to the sun. You point it to the sun and leave it there. It will just go on pointing to the sun. The satellite, of course, will not be just at one point. It will be in the orbit around this point. It just keeps on the sun. And these uninterrupted observations are very important. Going on it, it's going to be launched in about, I would imagine about 1.5 years from now. And then it has got various payloads and study as a photosphere, the chromosphere, and the corona. And the solar ultraviolet imaging telescope, which is being built at America, collaboration with several other institutes and ISRO. So this will produce simultaneously measure and monitor ultraviolet radiation, simultaneously mapping the photosphere and chromosphere with 11 filters. So you can see a series of filters which are shown here, and you'll get the image of the sun in all these filters, and getting it at different wavelengths means that you can combine them all together to get information about the color, about the thermodynamic conditions which are present there. And another large instrument called a visible coronagraph, a coronagraph where you use an aperture to remove the sun from the image, and then you observe the rest of it. This is the instrument which is being built in the Indian Institute of Astrophysics in Bangalore, again in collaboration with various institutes. This will be launched in 1.5 years, and then it will be there. There are several other also. There's something which is going to measure, again, polarization of X-rays. It's a satellite which is being set up. And the idea in setting up the satellites is that you tune them to a particular function, you keep it low, so it can piggyback mission. What it means is that the same rocket which carries other larger can carry your satellite also, so this rides free. There are 100 satellites like this. Some of them are, of course, very small. And this X-ray polarization mission, the instrument being built at the Raman Research Institute, is going to be launched. So now, a couple of questions. So a very exciting mission, which is actually being led from Varun Bhalerao and his colleagues at the Indian Institute of Technology in Bombay. It's not Indian Technology, it's in Mumbai, but it's called Indian Institute of Technology, Bombay. And this mission is to detect gamma ray bursts. So the idea is that you put gamma ray detectors on them. So one will look up to the sky, and the other will look at the other sky, and then they'll be going hitting the Earth in opposite directions. Okay, so it's, purpose of this mission is to discover over 150 high energy counterparts of gravitational wave detections. Some of you know that gravitational waves were first announced in 2016, and so these are the two merging black holes. Soon after that, merging neutron stars were observed, and merging black holes do not emit anything because only black holes are involved. But when you have two merged neutron stars, they emit a gamma ray burst. And then the gamma ray burst is followed by the detections in various bands. So now the idea is to detect such gamma ray counterparts of these bursts. And do that. But it also, since it is anywhere in orbit, will detect thousands and thousands of other faint off-axis gamma rays. Which got delayed because of the COVID effects, but it's picking up speed now. The other very important mission is going to be the next ultraviolet optics, which is being led from Bangalore. As resolution imaging done at the Indian Institute of Astrophysics in Bangalore, and that we have got the very the ultraviolet imaging astrosat, and now we're very enthused into building a larger telescope. So this will be the 1 meter aperture. The UVIT has only a 37 centimeter aperture. This will be done again in collaboration with various institutes, and you can see preliminary design. This is a couple of years old design. They have moved forward now, and so that the things are coming from space, landing onto the mirror, and it reflected to the secondary mirror, and even so there are a few other missions. For example, there is a mission to build a radio telescope, small radio telescope, and far to the moon, and land on the moon and keep it there. That is because at the specific wavelengths which are to be observed by this particular telescope, there will be a lot of Earth. So, so you can't observe at that wavelength on Earth. The background will be too high. You can't observe from the far side of the moon. From where the Earth, do not take the detections in the space and make the observations. I'll now talk with few about the expertise developed through these missions. So these astronomy missions, first we saw the space technology missions. They all involve engineering, they involve instrumentation, they involve extreme software development, data analytics, and project management. To do a project with
Hello, Ajit, can you hear me? Hello? I think he's having a bad connection. So I was following the talk, so I think it's mostly done. So if there are any questions, please feel free to put it up in the chat box. Okay, it's trying to call me. Hello? I'm muted. So am I audible?
Yes, sir.
So Ajit, are you there to take up a question? I didn't even see Siddharth, so maybe there's
Yeah, I'm here.
Okay.
Ajit, are you there? Hello?
We can't hear you actually. So, okay, it's a bit difficult because I think the connection is probably lost. Aniruddha Singh has a bunch of questions and maybe others as well. So,
Yeah. Hello, Ajit, can you hear us?
hello? Are you connected? Because I don't think we are able to hear you. So you logged off because there's some. Acha, ठीक है. What we'll do, we'll take up the questions later on then. Yeah. Okay, thanks. Bye. Okay, so I think it's a bit of a issue because of this really bad connections which I did have. What we'll do, we'll collect these questions, and if you have any more, please send us those, and we'll collect them. And Indrendra, can you just make a note on the questions, and we can probably get back to you on it once we get some reaction to that. Anybody else who want to ask Ajit a question, please just post it to us in the chat box, and we'll try to get him to reply to those. Thanks a lot. Sorry for the trouble. It's just logistics are not under our control. Internet connections vary from place to place from time to time, and we have to be patient. So thanks a lot that at least he managed to give a talk. He had this little bit wide outage of the first of all power, then successively the network was out. So, but luckily he joined over internet, over the mobile device, and just gave the talk, which is good. Okay, this brings us to the end of all the 30 lectures sessions we planned for this winter school. Thanks all for joining, but we have I think concluding session coming up, so stay tuned for that if you want. Over to Bhupeshji. Please take over, sir.
Okay, thank you, sir. Now we'll start the validity function. Dr. Lai Sharma will over you.
Yes, I am Dr. Rajesh Sharma, Group Head, Astronomical Observatory and Planetarium, Ujjain, MP Council of Science and Technology. Today is the validity function. The time has come to draw a curtain to our program as we come to the close of it. A very good evening and warm welcome to all of you to this validity session of the second winter school on observational astronomy. Last 2 weeks, we had deep insight in the several dimensions of astronomy and astrophysics. We had eminent scientists, educationists from MP and outside MP enlightening the participants. Thank you very much to you all. As rightly said, a pessimist complains about the wind and optimist tries to change it, and a leader adjusts the sail. The sail for this particular notion were adjusted by a person who is not only great motivation to all of us, but a visionary and a person who gave us the belief to bring together this event. He is none other than our Director General, Dr. Anil Kothari ji. May I take the pleasure of requesting our respected Director General, Gopal, MPCST Gopal, to deliver the welcome remarks.
हेलो शर्मा जी,
यस सर।
कब शुरू करना है?
जस्ट ज्वाइन कीजिए ऑन
है
सर आप वेलकम लेटर दीजिए सर।
अच्छा, आपने मुझे इनवाइट कर लिया?
यस सर यस।
मैं बोलता हूँ फिर से सर।
अच्छा अच्छा अच्छा, ओके, सॉरी सॉरी, मैं आई कुड नॉट हियर। ओके देन मैं एक्चुअली आई वाज कॉलिंग प्रवीण जी कि वो आए कि नहीं आए। तो मेरी आवाज आ रही है?
यस यस यस।
तो मैं शुड आई स्टार्ट सर? दत्ता सर, शुड आई स्टार्ट? ओके, सो वेरी गुड आफ्टरनून टू ऑल। ये जो 2 वीक सेकेंड विंटर स्कूल ऑन ऑब्जर्वेशनल एस्ट्रोनॉमी का एक बहुत ही इम्पॉर्टेंट प्रोग्राम फॉर रिसर्चर्स, फॉर पीजी स्टूडेंट्स and for others those who are interested in this area. मध्य प्रदेश काउंसिल ऑफ साइंस एंड टेक्नोलॉजी और इंडियन इंस्टीट्यूट ऑफ टेक्नोलॉजी इंदौर और इंडियन इंस्टीट्यूट ऑफ एस्ट्रोफिजिक्स बेंगलुरु, तीनों के द्वारा जो संयुक्त रूप से इस पिछले विगत 2 सप्ताह से ये कार्यक्रम विंटर स्कूल का चल रहा था, इसमें इसके जो आज वैलिडिटी प्रोग्राम है हम लोगों का, कि इस पूरी यात्रा का आज अंतिम पड़ाव है जब हम समाप्त करने जा रहे हैं इस कार्यक्रम को। आज हमारे बीच में इस अवसर पर चीफ गेस्ट के रूप में डॉक्टर सोमक राय चौधरी जी, ऑनरेबल डायरेक्टर ऑफ आयुका पुणे, रेनोल्ड साइंटिस्ट इन दिस एरिया, श्री प्रवीण रामदास जी, नेशनल सेक्रेटरी ऑफ विज्ञान भारती, हमारे बीच में उपस्थित हैं, जिनका सहयोग हमें बहुत मिलता रहा है और शुरू से इस कार्यक्रम में साथ हैं। ऐसे डॉक्टर एन रत्नाश्री, डायरेक्टर नेहरू प्लेनेटोरियम न्यू दिल्ली, इस प्रोग्राम के जो मैं कह सकता हूं कि आर्किटेक्ट हैं, हमारे आईआईए बेंगलोर के ऑनरेबल प्रोफेसर पद्माकर परिहार सर, ऑनरेबल डॉक्टर अभिरूप दत्ता सर फ्रॉम आईआईटी इंदौर, डॉक्टर राजेश शर्मा जी फ्रॉम एमपीसीएसटी भोपाल, डॉक्टर भूपेश सक्सेना जी, एमपीसीएसटी अगेन एमपीसीएसटी भोपाल, और इस अवसर पे हम लोगों के बीच में बहुत ही महत्वपूर्ण भूमिका जिनकी इस प्रोग्राम के लिए रही आयोजन में, ऐसे श्री संजय गुप्ता जी, आलोक जी फ्रॉम आर्यभट्ट फाउंडेशन, जिन्होंने बहुत एसोसिएट होकर इस प्रोग्राम को सक्सेसफुल बनाने में अपना एक इम्पॉर्टेंट कंट्रीब्यूशन दिया, और हमारे बहुत ही यंग एनर्जेटिक फेलो इंद्रेंद्र जी, और साथ ही मैं यह कहना चाहूँगा कि आईआईटी इंदौर के जो एस्ट्रोनॉमी, एस्ट्रोफिजिक्स और स्पेस इंजीनियरिंग डिपार्टमेंट की सारी फैकल्टी है, दत्ता साहब के नेतृत्व में, जिन्होंने इस पूरे प्रोग्राम को सफल बनाने में एक बहुत परिश्रम किया। ऐसे ऑल ऑनरेबल फैकल्टी मेंबर ऑफ आईआईटी इंदौर और फैकल्टी मेंबर ऑफ आईआईए बेंगलुरु, आयुका पुणे की भी कई फैकल्टीज ने इस प्रोग्राम में पार्टिसिपेट भी किया, एनलाइटन भी किया पार्टिसिपेंट्स को। इस कार्यक्रम में भी उपस्थित हैं वो सभी लोग। मध्य प्रदेश काउंसिल ऑफ साइंस एंड टेक्नोलॉजी के साइंटिस्ट जो इस प्रोग्राम में जुड़े हुए हैं, और सबसे इम्पोर्टेंटली ऑल पार्टिसिपेंट्स जिन्होंने पूरे लास्ट ड्यूरिंग 2 वीक्स में इस प्रोग्राम को बहुत कॉन्सेंट्रेट होके पार्टिसिपेट किया और इस प्रोग्राम को सक्सेसफुल बनाया। सो ऐसे ऑल पार्टिसिपेंट्स, ऑन बिहाफ ऑफ all organizing committee, it's time to welcome you all। कि हम इस समापन अवसर पे उपस्थित हैं सब, आप सभी का अभिनंदन, स्वागत है। यहाँ मैं बस इतना ही कहना चाहूँगा इस अवसर पे कि हम बहुत दिनों से इस तरह के कार्यक्रम को, पिछले साल भी हमने विंटर स्कूल किया था, वो फिजिकल किया था, उसमें हमारे ऑब्जर्वेटरी में पार्टिसिपेंट्स आए थे और वो कार्यक्रम हमने संपन्न किया था। इस बार हमारे सामने बहुत चैलेंजेस थे कि हम ऑनलाइन मोड में किस तरीके से इस कार्यक्रम को कर सकते हैं, लेकिन हमारे जो आर्किटेक्ट ऑफ द प्रोग्राम्स हैं, डॉक्टर दत्ता साहब, डॉक्टर परिहार साहब, डॉक्टर सक्सेना साहब, राजेश शर्मा जी, इस प्रोग्राम को इतना बढ़िया डिजाइन किया। पिछले 30 सत्र में मैं ये कह सकता हूँ, मैंने खुद लगभग सत्र में रहा हूँ, कि पूरे देश के सर्वश्रेष्ठ एक्सपर्ट्स इस फील्ड के हमारे पार्टिसिपेंट्स को उपलब्ध हुए हैं। उनको इससे ये ट्रेनिंग बहुत ही महत्वपूर्ण रोल अदा करने वाली है उनके नॉलेज बढ़ाने के लिए, एज वेल एज देयर कैरियर पॉइंट ऑफ व्यू। और ये हमने प्रोग्राम ऑनलाइन मोड में और इस बड़े स्तर पे सबके सहयोग से ही हम कर पाए हैं। मध्य प्रदेश काउंसिल ऑफ साइंस एंड टेक्नोलॉजी में हम बरामीर एस्ट्रोनॉमिकल ऑब्जर्वेटरी है हमारी, और साथ ही उज्जैन में हम एक प्लेनेटोरियम भी रन करते हैं। साथ ही बहुत नियर फ्यूचर, वेरी सून, हम एक 3D थिएटर और साइंस सेंटर अपने प्लेनेटोरियम में हम लाने वाले हैं उस कैंपस में। साथ ही इनोवेशन सेंटर इन द फील्ड ऑफ एस्ट्रोनॉमी, ये भी हमारा एक लक्ष्य है। हम इसमें भी प्रयासरत हैं कि किस तरीके से हम अपनी ऑब्जर्वेटरी को हमारे सारे एक्सपर्ट्स के सहयोग से, उनके गाइडेंस से हम इसको और अपग्रेड कर सकें, और इस तरीके से हम इस आईआईटी के साथ, आईआईए के साथ में, आयुका के साथ में, इस पूरे क्षेत्र में हम एक इंटरनेशनल सेंटर फॉर रिसर्च एंड एजुकेशन, जहां हम स्टूडेंट्स को, रिसर्चर्स को और इस फील्ड के और सभी जो जुड़े हुए लोग हैं उनके लिए, और एक आम लोगों के लिए जिनकी क्यूरियोसिटी है, जो इस क्षेत्र में बहुत ही उत्सुकता के साथ कुछ जानना समझना चाहते हैं, एक सेंटर सबके सहयोग से हम डेवलप करने के लिए कमिटेड हैं। और हम विश्वास दिलाते हैं कि बहुत जल्दी हम इस तरीके का सेंटर और जो नई हमारी योजनाएं हैं उसको हम पूरा करेंगे, और साथ ही इस तरह के प्रोग्राम जो स्टूडेंट्स के लिए, स्कूल गोइंग स्टूडेंट्स से लेके और यूनिवर्सिटी स्टूडेंट्स तक, रिसर्चर्स के लिए और कॉमन पीपल के लिए, जो उनकी क्यूरियोसिटी है, जो उनको एक अवेयरनेस और ओरिएंटेशन साइंटिफिक करने के लिए हम एक श्रृंखला प्रोग्राम्स की हमारे सभी एक्सपर्ट्स की टीम के साथ जुड़ के एक प्लानिंग के साथ में हम करेंगे। हमारे डिपार्टमेंट ने बहुत अच्छा काम किया। हमारे राजेश शर्मा जी, भूपेश जी एक बहुत अथक परिश्रम से इस मुकाम को, इस पूरी यात्रा को हम सफलतापूर्वक यहाँ तक लाए हैं। इस अवसर पे मैं आप जिन्होंने भी इसमें हमें सहयोग किया, पार्टिसिपेट किया, ऑर्गेनाइजिंग कमेटी की ओर से मैं सबका धन्यवाद भी अदा करता हूँ, अभिनंदन भी करता हूँ। एक बार पुनः सबका इस आशा के साथ स्वागत करता हूँ कि भविष्य में भी हम इस तरीके के प्रोग्राम आप सबके सहयोग और मार्गदर्शन से करते रहेंगे। थैंक यू वेरी मच टू ऑल। स्पेशली आई एम थैंकफुल टू डॉक्टर सोमक राय साहब, जिनका भी हमको गाइडेंस और जिन्होंने समय भी दिया। हमारी एक वेरी शॉर्ट स्पॉन ऑफ टाइम में के नोटिस पे हमें समय दिया उन्होंने इस प्रोग्राम के लिए। सो थैंक यू वेरी मच टू वंस अगेन ऑल। समस्त आईआईटी की फैकल्टी को भी, स्पेशली दत्ता साहब को मेरा बहुत बहुत धन्यवाद, परिहार साहब को बहुत बहुत धन्यवाद। सो थैंक यू। ओवर टू शर्मा जी, प्लीज।
Thank you, sir, for your visionary remark about planetarium observatory and the winter school, sir. Thank you, sir. This winter school was made possible by many hands, hearts, and minds working together to express a word of appreciation and gratitude. We have with us Dr. Abril Datta. May I like to request Dr. Datta kindly present the report on winter school. Please, Dr. Datta, sir.
Just give me a few seconds.
Sure, sir.
Sharing the slide. Huh? Okay. Okay. Okay, can you see my slide? Slide share ho?
Yeah, it seems like.
Okay. So yeah, thanks a lot, Anilji, for being such a huge support and the driving force to conduct this second winter school on a virtual mode. And initially, we were very troubled to understand how to do this. So there were quite a bit of discussion, but finally, I think we went ahead. So thanks to the three primary organizing institute. So thank Dr. Anilji from MPCST and Professor Nilesh Jain from Director IIT Indore and Professor Annapurni Subramaniam, who is Director IIA Bangalore. We came up with this kind of very huge plan of splitting up 7 or 10 days of in-person lectures, hands-on training into 2 weeks, 10 days of lectures, of 3 lectures each day. And but it finally, except one lecture which we have to reschedule on a separate day. And today's last lecture just because of the little bit of a fluctuation in the network. All others went very well, and a lot of presentations were also streamed over YouTube, and I think there were questions from both YouTube channel as well as on the WebEx. So I think it went well. Regarding the participations, the participants came from all across, not only MP, but also from other different states. This is roughly the participation, registered participants from different institutes across MP, and there were participants from IIT as well. But the most encouraging thing is that the gender ratio of the participants, it was 49% of female participant versus 51% of male participant, which is really encouraging nowadays that astronomy is doing so well to balance this ratio in among the students. That's the strength, and I hope it continues. A little bit of distribution across the state-wise, and so from different places, how many people came, just to have a demographic kind of advantage. Now coming to the program, we have a very ambitious program asking for only the person who was leading the research and topic in the entire India and also around in the world. But all of them, most of them agreed on a very short time. So they all agreed to deliver the lecture, given it is that the directors of current directors of institutes, past directors of institutes, and they are all busy people, but they all find out time to come join us online and deliver the lecture. So that's quite remarkable. I thank all of them for such a supporting our efforts, and they gave excellent lectures. I hope this remains in YouTube, and also people can go back and check the lectures again and again. And hopefully we'll come back with an exciting edition next year again on this. Okay, so yes, the collage of all the people who are involved in delivering lectures in the institute. It is done by one of my students, Indrendra, who has just put all this together, the demographic maps. So I think it went very well, and we look forward to the next year. I hope all of you enjoyed it. I thank all the speakers and all my colleagues from IIT Indore who were a really strong support. Without them, we wouldn't have been able to find coordinators for each day. They took out time from their afternoon sessions of the daily schedule and have been over here. So thanks everyone. Whoever is here, whoever not here, Siddharth's photograph is not here, so I thank Siddharth also for doing quite a good support. So I stop here and over to Dr. Bhupesh for taking the program further. Thank you. Thanks a lot.
Nice combination and decent presentations. The way you have done. Thank you, sir.
Thank you.
We are happy to have with us Dr. Padmakar Parihar, IIT Bangalore, who himself has a deep interest in the field of astronomy. May I kindly request Dr. Padmakar Parihar to share a few words.
Sarmaji, thank you for asking me to say a few words. I would say that this 2 weeks long winter school ended today. Very successful program it was. Very successfully organized and conducted by MPCST as well as IIT Indore. If you have to give the credit for this program, then I would say that 90 to 95% credit goes to MPCST and IIT Indore. Only 10 to 5% credit can be given to IIA to to my institution. Otherwise, the full credit goes to both of you, both of these two party. The one very surprising thing which is happening slowly is the emergence of a new center for astronomy and astrophysics in central India. Otherwise, if you look at the map of India and see where these centers are located, the Center for Astronomy and Astrophysics, then none of them are in central India. But in the form of IIT Indore Astronomy and Space Physics Department, as well as Ujjain Observatory, we can see a slow emergence of a new center in central India, and that is really very interestingly happened over a very long wait, we can say, because we were expecting to see an observatory in Pachmari. It's now history, but I would say the dream is slowly fulfilling. I hope that this is just beginning, and in coming years, many such programs will be jointly organized by IIT Indore as well as MPCST, and I would say both of you are really good partners. So keep it up. The one thing I want to say before I stop saying something, and that is we are really very pleased to see Dr. Kothari ji as a leader for MPCST now, who is very keen to actually improve the facility in his system and specifically the observatory. So I hope that Kothari ji, having very active supports from Rajesh Sharma ji and Bhupesh ji, will take observatory to new level, and it will be really a center for excellence in central India. So by this, I would just stop here, and Sharma ji, you can now take over.
Dr. Karim, your insightfulness on the winter school as well as the future of the astronomical observatory. Thank you, sir. Now, we want to make slightly modification in the order of the program. We can take the feedback from the students. That is a very essential component to the justifying the winter school. So, I like to invite to share the experience first to Mr. Dhaneshwar. He is from Physics Department, Pandit Ravi Shankar Shukla University, Raipur. Mr. Dhaneshwar.
Yes, sir. Thank you, sir.
Yes. Open your camera also.
Yes, sir. Good evening to all of you. मैं दानेश्वर भंडारी पंडित रविशंकर शुक्ला विश्वविद्यालय रायपुर छत्तीसगढ़ का छात्र हूँ।
धनेश्वर जी, आप अपना कैमरा खोल सकते हैं।
सर एक्चुअली नेटवर्क प्रॉब्लम।
ओके कंटिन्यू। यस।
मैं इस कार्यक्रम सेकंड विंटर स्कूल ऑन ऑब्जर्वेशन एस्ट्रोनॉमी 2021 को आयोजित करने वाले एमपीसीएसटी, आईआईटी इंदौर, आईआईए बेंगलोर के समस्त प्रोफेसरों, डॉक्टर अनिल कोठारी, डॉक्टर भूपेश सक्सेना, प्रोफेसर योगदान को करता हूँ। मैं अपने हमारे विश्वविद्यालय के डॉक्टर इनके चक्रधारी बहुत ही आभारी हूँ, जिन्होंने मुझे वर्कशॉप से जुड़ने के लिए प्रेरित किया। इस विंटर स्कूल में संचालित होने वाले ऑनलाइन लेक्चर से मुझे बहुत कुछ जानने और सीखने को मिला, जो मेरी जिज्ञासाओं को और बढ़ाने में सार्थक रहा, जो मेरे भविष्य के लिए बहुत ही उपयोगी साबित होगा। मैं वर्तमान समय में इस विषय विशेष पर बहुत अधिक रुचिकर हूँ। इस कार्यक्रम की हर एक लेक्चर विषय जो बहुत ही ज्ञानवर्धक एवं प्रभावपूर्ण रहे। इनमें से कुछ लेक्चर जिन्होंने मुझे बहुत अधिक प्रभावित किया, उनमें सर्वप्रथम मैं प्रोफेसर जी.सी. अनुपमा मैम, जिन्होंने बताया कि स्टार का फॉर्मेशन और उनका डेथ कैसा होता है। यहाँ मुझे स्टार की लाइफ साइकिल के बारे में जानने को मिला, और साथ साथ अन्य लेक्चर जैसे कि सन इन नेबरहुड प्रोफेसर दीपांकर बनर्जी सर द्वारा दिया गया, जिसमें मुझे सन के इंटरनल स्ट्रक्चर, कोरोना, पीएमई, सन स्पॉट के बारे में जानने को मिला, और एशियन एंड ब्लैक होल्स के बारे में डॉक्टर प्रीति मैम द्वारा, और फिर मेरा इंटरेस्टिंग सब्जेक्ट रहा जो ग्रेविटेशनल एस्ट्रोनॉमी रहा, जो प्रोफेसर अभिजीत सर द्वारा दिया गया। जब से मुझे GW के पता चला, इसमें विशेष रुचि रहा कि इसका प्रेडिक्शन कैसे करते हैं, इसका फ्यूचर में क्या उपयोग है, जो मेरी जिज्ञासाओं को बढ़ाने के साथ साथ पूर्ण भी करता है। फिर मेगा साइंस प्रोजेक्ट जो प्रोफेसर यशवंत गुप्ता सर द्वारा दिया गया, जिसमें हमारा कंट्री इंडिया लार्ज प्रोजेक्ट जैसे TMT, SKA, लाइगो इंडिया जैसे प्रोजेक्ट में भागीदार है। साथ ही आज चेरेंको टेलीस्कोप अरे, जो कि काफी इंटरेस्टिंग रहा, जो प्रोफेसर अमित शुक्ला सर द्वारा दिया गया। फिर हम लोगों ने डोंगला वर्चुअल विजिट भी किया। ये मेरे फर्स्ट टाइम था कि किसी ऑब्जर्वेटरी को अंदर से देखा और इसको कैसे ऑपरेट करते हैं ये देखा। साथ ही में ग्राउंड स्टेट में छोटा टेलीस्कोप भी था, जो सन स्पॉट ऑब्जर्वेशन के लिए रखा गया था। हम लोग कोरोना पेंडेमिक की वजह से फिजिकली विजिट नहीं कर पाए। अगर भविष्य में मुझे ऐसा अवसर मिलेगा तो अवश्य डोंगला ऑब्जर्वेटरी विजिट करना चाहूँगा और भविष्य में उसमें काम करना चाहूँगा। इस कार्यक्रम के अंतिम दिवस पर फीडबैक की मंच प्रदान करने के लिए मैं आप सभी का आभारी हूँ। यह द्वितीय विंटर स्कूल मेरे जैसे अन्य इच्छुक छात्र छात्राओं के लिए बहुत ही लाभदायक एवं प्रेरणादायक रहा। आशा करता हूँ ऐसा कार्यक्रम हर सत्र आयोजित होता रहे और हमारे जैसे अन्य छात्र छात्राएं लाभान्वित होते रहें। साथ ही भारत में खगोल विज्ञान को नई ऊंचाइयां मिलती रहे। इन्हीं अंतिम शब्दों से अपनी वाणी को विराम देना चाहता हूँ। धन्यवाद।
Thank you for sharing your nice experience. Now may I like to invite to share the experience Ms. Kriti Agrawal, Institute of Excellence for Higher Education, Bhopal. Kriti Agrawal. Kriti Agrawal, can you hear me? Okay, next I would like to invite to share the experience Mr. Aniruddha Singh, Jivaji University, Gwalior.
Okay, greetings of the day, sir. Am I audible to you, sir? Am I audible, sir? Yeah.
You can open your camera.
Okay. Okay. Greetings of the day. Myself, Anirudh Singh. I am a student of MSc final in School of Studies in Physics, Jivaji University, Gwalior. Sir, I feel privileged to be a part of this second winter school on observational astronomy. I actually enjoyed while going through the module of this course. All the lectures were very exciting, enlightening, and actually intellectually challenging lectures. I have gained a lot of knowledge and a sufficiently broad view of the astronomy. Actually, I'm interested since beginning of my graduation, and my professor Dr. D.C. Gupta suggested me to join this observational astronomy winter school because it was actually conducting online. I would say that this would be actually the true implementation of tagline "Aapada mein Avsar," because in this hard Corona times, it is impossible to get in-person present. However, technologically we joined and enjoyed this program. First of all, I would like to say that lectures were very interesting. but some internet issues were there, I found. So I hope that in future they will not be there. And many doubts that I have in my mind are actually cleared within the talks of various speakers. So definitely I would recommend all these lectures to one who is interested in astronomy. I would request MPCST and other organizing committee that if possible, please organize other such lectures, especially on quantum mechanics and so once again, I'm thanking to the all organizing committee and so for organizing such a wonderful event. Thank you, sir. Okay. So I too rest my audio.
Okay, next I like to request Miss Anamika Lodhi. She is from Holkar Science College, Indore. Anamika Lodhi.
Am I audible?
Yes, yes, audible. You can open your camera also.
Sir, there is network problem, so.
Okay, okay.
Good evening, everyone. My name is Anamika Lodhi, and I am from Holkar Science College, Indore. I came to know about Dongla Observatory through my friends who visited this wonderful observatory last year. Before attending this webinar, I have only a little knowledge in this field, but now I am full of curiosity and enthusiasm. Not only has the webinar organized in extremely professional manner, but all the information that all professors share us, from this we have learned a lot of things like galaxies, sun, stars, and many more, which gave us a new perspective in the field of astronomy. And via this seminar, I got a chance to listen amazing professors. From day one, I am learning new and mysterious things about this universe and our galaxies. This program is, of course, a unique one of its type. I will definitely explore more and more in this field. Thank you all professors, and also thanks to our coordinators. Sir, thank you so much. Permit me to attend this wonderful online winter school organized by the Dongla Observatory, MPCST Bhopal, IIT Indore, and IIA Bangalore. Thank you, sir. Thank you.
Neeraj Patel, APS University, Rewar, Department of Space Physics. Neeraj Patel. Mr. Neeraj Patel.
कॉफी ऑर्डर करूँ भी लोग
नीरज पटेल फोन उठा रहा था
Okay.
शर्मा जी आगे बढ़ाइए प्रोग्राम।
It is my pleasure that we are have among us Dr. Praveen G. Ramdas, National Secretary, Vijnana Bharati. May I request to him kindly share his words on the occasion of the valedictory section of the winter school. Shri Praveen G. Ramdas.
Namaste. Am I audible?
Yes.
Yeah. आज के इस कार्यक्रम में ये जो विंटर स्कूल का जो आयोजन हुआ है उसके समापन कार्यक्रम में मुझे जुड़ने का मौका मिला। इसके लिए मैं आयोजकों को बहुत बहुत धन्यवाद देता हूँ। कहीं ना कहीं विज्ञान भारती के साथ कार्य करते हुए डोंगला में ये जो ऑब्जर्वेटरी बना उसका जो रिलेवेंस और उसका जो इम्पोर्टेंस ये सब के बारे में मुझे विज्ञान भारती के कार्यकर्ता के कारण मुझे समझने का एक मौका मिला। ये एक बहुत बड़ा हमारा देश के एक बहुत बड़ा एक इम्पोर्टेंट ऑब्जर्वेटरी है। कहीं ना कहीं हमको इसके बारे में बहुत साल पता नहीं था, फिर इसके बारे में जानकारी मिला और मध्य प्रदेश शासन ने आगे बढ़ाया और एक विश्व स्तरीय ऑब्जर्वेटरी के रूप में उज्जैन और डोंगला का ऑब्जर्वेटरी का स्थापना हुआ। इसका जो एक सदुपयोग होना चाहिए, इसका रिसर्च के लिए बहुत उपयोग होना चाहिए, इस तरह की चर्चा बहुत साल से आगे चल रहा है। मैं महानिर्देशक और उनका टीम को पूरा साधुवाद देता हूँ। आईआईटी जैसा एक उत्कृष्ट संस्था के साथ मिलके एक बहुत अच्छा, मैंने इस कार्यक्रम में जितने भी वक्ताओं का नाम देखा, उनका जो सब्जेक्ट सब देखा, बहुत ही प्रभावी ढंग का एक कार्यक्रम मैपकॉस्ट और आईआईटी इंदौर मिलके किया। उसको मैं बहुत बहुत धन्यवाद देता हूँ, इसके मैं बहुत बहुत साधुवाद देता हूँ और अभिनंदन भी करता हूँ। मैं बहुत ज़्यादा समय ना लेते हुए, अब मुझे पता है कि इसके बाद माननीय सोमक राय जी का उद्बोधन है, तो मैं सभी को साधुवाद देते हैं। इस तरह की कार्यक्रम देश के उत्कृष्ट संस्थाओं के साथ मिलकर करना चाहिए और ये एक बहुत अच्छा शुरुआत है। इस शुरुआत से ऊर्जा लेके बहुत अच्छे से आगे बढ़ना है। इतना ही बोल के मैं मेरा इस वाणी को विराम देता हूँ। वंदे मातरम।
रोहित जी बहुत बहुत धन्यवाद। आपने जो विजन दिया है उस पर हम लोग सही आगे भी काम करेंगे और जो है एस्ट्रोनॉमी की फील्ड में जो है मध्य प्रदेश को और देश को आगे ले जाएंगे। बहुत बहुत धन्यवाद प्रवीण जी। डॉक्टर रत्नाश्री जो है टेक्निकल प्रॉब्लम कारण जुड़ नहीं पा रही, उनका 2 बार फोन आ चुका है मेरे पास कि शर्मा जी देयर इज अ प्रॉब्लम। तो सो वी प्रोसीड फर्दर फॉर दिस validity session program. The fragrance of the flower is spread only in the direction of the wind, but the goodness of the person is spread in all directions. Gentlemen, ladies and gentlemen, we are delighted to have with us Dr. Somak Rai Chaudhary as Honorable the Chief Guest of the validity ceremony. May I request to you kindly address the gathering, Dr. Chaudhary. Sir, welcome you, sir.
Sir, your voice is not clear.
Am I now audible? Is that all right? Yes. Okay. Namaskar. Good evening. As I said, I'm very honored to be part of this winter school, not just as a chief guest at this session, but also I've taken part in giving one of the lectures, as well as attended many of these lectures, and they've actually been absolutely wonderful. I missed visiting the Dongla, and for a long time I've been talking to Kothari ji and various other people for visiting your observatory and also various other places of interest nearby. And I hope that very soon we will be able to go there. But this also gives a wonderful opportunity to online network with a lot of people all over central India, as well as many other places within the country, which is also wonderful. During this year, we have had this disadvantage of being interned where we are, but it has also expanded our scope of networking with so many people everywhere. So we see the positive side to this online interaction as well. We can't be there in person, but we are in there with our soul, and we are interacting with so many people, which is not possible in a just look at this amazing confluence of all these institutions that have come together to create this winter school. In my entire life, I've never seen a planetarium, an observatory, an IIT, and a DST institution like IIA coming together to organize a winter school. This is absolutely unique. The other unique thing, and all schools like this, all actually the courses like this should have a unique selling point. And the other uniqueness of this particular winter school has been, in addition to planetariums and observatories and institutions coming together, is the focus on the history that this winter school has had. Not only history of Indian astronomy, but history of the local observatory, history of local interesting things in and around where this is being held. Even though we are in cyberspace, in what we call this entire virtual space, we've talked about in various talks, in Professor Bhaya's talk, in Professor Ratnashri, and then Professor Shailaja's talk the other day, and initially in Professor Pandey's talk, we've talked about the amazingly rich heritage we have in traditional astronomy here, as well as the archaeological and architectural features that are there in and around the host institutions, as well as elsewhere in India. To bring together that kind of astronomy, to look at the architectural and archaeological angles of astronomy, plus looking forward to the physics part of astronomy, this coming together was absolutely wonderful in here, I think. And this, I think, you should, going forward, keep this flavor, so that even if we are in virtual space, we are rooted in the locality where you are. As Dr. Parihar said very nicely, that there is a very interesting collaboration and conglomeration happening in central India right now, in bringing together research institutions to work and build new facilities. And in Indore, Ujjain, there are some amazing things happening, as I can see. I am myself involved in LIGO India, for example, about which you heard. And LIGO takes a very important presence in Arakat, in Indore, as well as IIT Indore. And we have from our UGC inter-university centers, we have another institution in Indore, which is the UGC DAE CSR, which is also growing very interestingly in allied areas and taking part in various other mega science projects. So having this, and LIGO India is also happening in central India, right? Even though it's in Maharashtra, it's in central India. And so I'm very, very supportive of these homegrown facilities on Indian soil that are taking place, that is looking big. And to establish these big mega projects, we need the involvement of the student population. We need the involvement of the university and college teachers, without whom, just in the institutions, the research institution, we don't have enough people to run these big dreams India now has in taking part in mega science. And that is why it is very important for a forum like this to bring together people who are interested in astronomy at all levels, at the planetarium level, at the observatory level, at the college level and university level, all together to come together and celebrate not only India's tradition in astronomy, but the current dreams and plans. And that is why I think it's very, very important for us to have programs like this. And I think you will keep this flavor and move forward together, but keeping in mind that we are opening up the eyes of the younger generation to what possibilities we have in Indian science. And I think this particular winter school did a very good job of bringing together some of the best scientists in the country to give talks and talk directly to the younger generation. This is absolutely fantastic. And this, of course, the online advantage we have gave us this advantage. Normally in a winter school, you would not probably have all these very good speakers come together in one event, but this is a stellar event, and this platform allows us to do this. I would recommend that even after the pandemic is over and we are going everywhere, that you might actually carry on having an online forum like this, where people can come together and interact even without going personally there. And this has given us an idea and an opportunity as well. So with those words, I thank you again for inviting me to come to this and take part in this wonderful event. And I hope you have you carry this on every year, and all your various activities, not just with this workshop, but the activities with the observatories as well as the planetarium, and the interaction with the universities, the IITs, and the other institutions actually thrive and take you forward. Thank you very much. Jai Hind.
Thank you, sir, for your influential message. We are charmed by your sharp fluency, sir. Thank you, sir.
Thank you.
I request to my colleague Bhupesh Saxena, kindly give the vote of thanks.
Okay. Thank you, sir. Thank you. Good evening to everyone present here. I would like to conclude the second winter school on observational astronomy with a vote of thanks. I am thankful to our special guest, Sri Praveen Ramdas, National Secretary, Vigyan Bharati, who has promoted science and technology in India through Vigyan Bharati. He has given valuable inputs for this event. I would like to express my thanks to our chief guest, Dr. Somakrai Jyoti sir, Director ICA Pune, for accepting our invitation and enlightening us with their presence. Thank you very much, sir. Especially, I am grateful to renowned eminent scientists who have delivered their lectures in ancient, medieval, and modern astronomy. I am thankful to Professor Padmakar Paryar sir, scientist, Indian Institute of Astronomy, Bangalore, for his valuable guidance and technical support. Many thanks to Dr. Abdul Datta, Associate Professor, IIT Indore, and his faculty members for coordinating our session and making this event possible. I would like to express my thanks to Dr. Anil Kothari, Director General, MP Council of Science and Technology, who has guided and motivated us to organize this successful event. Now, last but not least, my sincere gratitude to all participants, Dr. Rai Sharma, Sir, Group Head, Ujjain Planetarium and Dungla Observatory. My special thanks to our IT team, Dr. Dharmendra Costa, Sri Javed Gaurav, Sri Lalit Kumar, Sri G.T. Dasmukh, Sri Alok, and Sri Sanjay Gupta from Harvard Foundation. I am thankful to Professor Meghawale and Sri Chakras Jain ji for coverage, publication, and media. Once again, thanks to all for cooperation throughout the event in second winter school 2021. We could encourage students to explore further in the field of astronomy and astrophysics. Thanks a lot. Thank you very much, sir. Open group photo.
Actually, there is a group photo. So I request to all the participants kindly open their camera.
Thank you, Dr. Somakrai Chaudhary, sir, for being with us.
Thank you, sir.
We are very much honored, sir, to have you.
I request all the participants kindly come on the camera.
Nobody's coming.
Thank you, Abhirup, for doing this academic program. It is very, very well done.
Thank you. Thanks a lot. Thank you.
Thank you, sir.
We wish to continue something like this. Come back. Actually, we are discussing to come back with the engineering aspects of astronomy, because we are from IIT, and so that's we'll see.
We organized one thing here in Ram Prakash has been doing a series,
right.
With one in Bangalore, and then in VIT in Pune we did one with hundreds of engineering students. I think this is a wonderful subject.
Okay. Yeah.
So not many people are putting their cameras on. Not interested.
Yes.
Okay.
Once again,
Students
are not coming forward.
Ratnasri ma'am, very good evening.
Yeah, am I audible now? My apologies. I had it. I don't know even now if I'm audible. Am
Yes,
I
you are.
audible?
You are perfectly audible.
Yes, yes.
I was having a very bad network connection for quite some time, and I just wanted to express my awe for the kind of a program which had been organized, and for this beautiful resource which has been created.
Yeah.
So now program we have completed.
Coming to our planet, in fact, so congratulations to the organizers for the program.
Okay.
Very much. Thank you very much, ma'am.
Thank you very much.
Thank you.
Madam, thanks.
Thank you, sir. Thank you. सभी को नमस्कार.
नमस्कार 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 चलो ठीक बोले थे आप सुनिए और फिर लिख के मैंने इसको क्या करा टाइप करा तैयारी करके नहीं आया ना तो नहीं अच्छा है नहीं चाहिए मैंने मतलब जो है मेरा करना ये अपन करते हैं तैयारी करते हैं बाद में